Okay, everyone. So here we go. So we have so far discussed out the idea of computer vision, the understanding of pixels, right? Pixels are fundamental parts of or segments of images. And the task in computer vision, which includes image classification, localization, object detection to object segmentation. And what exactly is classification is where we have lots of images with the labels, whether those images are cat or dog or maybe different other objects, and how do we use those images to train a neural network which can learn how the specific object looks like. And for any new image, it can be used, the neural network can be used to classify that what is the object in that particular image. We've seen the idea of what is deep learning in context to that, how is it different to machine learning, and deep learning typical applications, the computational resources required for deep learning, and what exactly deep learning algorithms are. So every deep learning algorithm is modification to the basic fundamental algorithm, that is neural networks. We also have taken basic understanding of neural network, a quick tour on neural network, but there's a lot more to study. If you haven't gone throughout neural networks, there's a lot more to get into. We started with the algorithm of the the topic of the workshop, which was convolution neural network. Understood the concept of convolution neural network. It is composed of two sections: feature detection and classification. We discussed out that feature detection section consists of three things: convolution, relay, and pooling. We understood the concept of convolution, how does that works out, the concept of filters and the filter size and the stride and padding, and how are these used to generate a feature map. What ReLU does, so it simply truncates the negative values to 0 and keeps only positive values in the feature map. And pooling pulls out the maximum value in a particular pool size, which is going to be 2 by 2, right? And that's how this whole process, convolution and pooling, helps in extracting features, which can then be used by a dense layer, which can learn from these features about how these features are useful in detecting the object image, whether it is 1, 2, 3, 4, 5, 6, 7, 8, 9, or it is male or female, or it is a car or truck or anything like that. It can be used for image classification for that purpose. Similarly, it can also be used for face recognition as well, I would say, right? So whether you want to do face recognition or face detection or any other type of image classification based task, this particular model can be used out, right? So that was about it, everyone. So let's go ahead and work with a use case on the top of this, right? And definitely that's going to be pretty much interesting. I'm going to actually work with show you a use case on small data set, right? I actually initially wanted to show you a use case on large data set, but on large data set, we'll be easily able to achieve good accuracy, right? So which is something that I don't want to achieve good accuracy, because then without good accuracy, if you work with small data set, how do you achieve good accuracy? That's what I wanted to show you in this workshop as well, right? So technically, when you go with sufficiently large amount of data and try to build a convolution neural network, you will easily be able to achieve good amount of accuracy, or you can say good performance on that, right? And it would be sort of easy to process, I would say, and to perform image classification or object detection task on large data set. So, but here in this case, I'm going to show you an example on small data set where you don't have large volume of data for a specific task, and how do you handle that situation, right? And in that situation, I'll bring the context of transfer learning, and we'll try to improve the performance of model. Okay. So I hope we are good so far, everyone, right? Good to go ahead and get started with that, right? So let's understand the problem that we're going to be solving up and the use case that we're going to be working with. Let me also, share my screen so that we all can, like this was the, not the main screen that I was sharing. And so let's understand the data set that we have here, and how do we use that data set, right? What is the data set and what is the problem statement that we have? So as a part of data, everyone, we have three types of pictures, right? So we have pictures of type dogs, right? We have pictures of type dogs, and so three types of pictures. We have a few pictures of dogs horses and humans. Right, so these are all the pictures of dogs, different shapes of pictures of dogs, as you can see that, different size of pictures we have, right? These all are dogs pictures. Similarly, in the horses folder, I have all the photographs of horses. Some of the photographs are internet downloaded, which is like a very generic photographs. Maybe the horse is not very well interpretable over here, right? So like this also you can say, right? Some of the pictures have a lot of challenges, as in the aspect ratio of horse compared to the part of the other picture, and the size of photograph as well, the part of horse which is visible or not, right? These are many challenges that we have as a part of our data, right? Humans also, we have a lot of pictures of humans, and many of these humans are riders, right? Most of the humans are in the rider dress, right? And these are lots and lots of pictures of humans. And there is also some confusing images. For example, some images, horses and humans are visible together. As you can see that here, in some pictures, horses and humans are visible together, but they're tagged as humans, right? And like this, you can say, all right, like this. And this is tagged as human photograph, this one as well, right? So there are some confusing pictures as well, where horses and humans are together. We also have similar situation in dogs as well. In some of the pictures of dogs, they are humans with dogs, which is a bit of confusing picture. So, this data set is very small, as we only have 200 pictures, 202 pictures for dogs, 202 pictures for humans, and 202 pictures for horses as well, right? Same number of pictures for all the three categories, but the volume is very less. As you can see, only 600 pictures we have on a whole around to train a neural network, which is very small volume of data. On this small volume of data, having this much complexity of pictures, where we have different size, different aspect ratio, mixed of images, mixed of features, confusing images, it is very difficult to achieve good performance on image classification, right? It's not super easy to train a neural network which can learn to identify different objects, right? And when you train that, when you have a bit simply clear data set and you try to train the model, you will be able to get good performance with convolution neural network. But then if you have very complex data set and very complex situation, much more a bit like this, where you have, still here I have 3 class classification, you may have 20 class or 100 class classification problem as well. In those situations, you may have a lot of challenges, and the way to get good performance may be a bit difficult task. Okay, so that's the idea, everyone. That's the understanding of the data set that we have. So I hope, are we all good with the understanding of what problem are we trying to solve? What is the objective? The objective is that we have around 202 images of dogs, horses, and humans. We need to train a neural network which can learn from this, and for any new picture, it should be able to recognize whether that is a dog, or that is a horse, or that is a human. Are we good with this part, everyone? Any question, any doubt you have on this, please let me know. In real life situation, you may not be having pictures in different folders, but in real life situation, you need to label data. All the supervised learning algorithms require label data. So either the name of picture should contain the name of object. For example, you see horse, 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 right? Or some way you have to be able to recognize them. You have to be able to prepare the label. Either you do that manually, arrange that into different folders, or you either rename all the pictures up to that. Because in order to train a neural network, you need to have label data. And to create label data, you will have to do either manual labeling or some smarter way of labeling. The other short way to do that, you can apply techniques like clustering. And using clustering, you can, if you have a mix of pictures, you can cluster them in a different buckets, and then you can label them easily. That is a shortcut approach for labeling. Right, so I hope that answers the question, Rahul. There's a question, what about both, like dog and human in this case, right? So in majority of the cases, those are tagged as the object which is most visible in that picture, right? For example, in this picture, if it is human is more visible, this is tagged as human at the moment. So algorithm is going to most learn the features related to human and make sense out of that. Right, but yes, it may happen that in a single image you may have two objects as well. Currently, we are dealing with single label classification problem, but yeah, we also do multi-label image classification, in which the algorithm is going to predicting the name of multiple images present in multiple objects present in the single image, right? And we call that as multi-label image classification. I hope we go to that, everyone. K-means K-means is an algorithm which is used for clustering mainly in data science, a bit more in pixels. On the pixel level, that means you can do color segmentation using K-means. But on the top of it, there are a lot of other algorithms which are widely used for segmentation, or you can say organization of pictures and images, right? Autoencoders are a very popular approach for doing the same. Other than that, you have self-organizing maps, a bit of it, right? So these are different pictures, different ways to do that. So autoencoders, they do what? They represent the data, which is pictures, in latent space format, where latent space vector format, where it is easily possible to see the pictures which are quite closer to each other, right? So autoencoders are a very smarter way of bucketing pictures and photographs, right? And they're part of they're part of neural networks. Okay. And in case you want to do segmentation within one image about multiple objects, that means in that case you can use K-means. So I want to do a retinal blood vessel segmentation. That means, Kalyan, what I understand is that you want to do in a single image, you may have different components, a blood vessel and something else, maybe background or some other component, and you want to do segmentation to be able to identify those components, right? If that's the situation, then one is the simpler approach to achieve this could be K-means clustering. If you want to also achieve extent of maybe blood vessel, or maybe if there is any other issue in that blood vessel, C-means clustering could be quite helpful as well, right? If you want to go one level above that. So K-means clustering is going to cluster your pixel into one bucket, whereas C-means is going to cluster your pixel into multiple buckets. So that is going to be more, I would say, more clear idea you will get out of the pixels. In case you want to go one level even up than that, the best approach or the most performing approach could be image segmentation using UNIT. So UNIT is a modification. It's a modification to convolution neural network, and using that we do instance segmentation, right? So that is also a very standard approach to go ahead about that, right? UNIT, more of if I have to show you, it kind of looks like. Right, so this is an example of a UNIT network. This we widely use for, so this is a neural network, convolution neural network, and we widely use it for segmentation, right? So this is one of the advanced method that you may want to use, right? So yeah, those are methods available which can be used. Starting point could be K-means, then you can shift to C-means clustering, and from there you can shift to segmentation using neural networks, where you can try out UNIT as well for that. Is latent space a gradient distribution of real image data? Much more like that, Vishnu. So if I have to show you an example of that latent space vector representation, it could be possibly to help you understand about that. Just a moment. So yes, it is more of a gradient distribution, you can say, right, one way. And so they are autoencoders which can be used to represent this. I mean, you can also think of them as a generic damage reduction approach, right? And are very powerful approach to achieve this, right? So if I show like that, you can see this is an example. So here standard autoencoders, which are used to represent in the form, images in the form of discrete gradients. Now this is the outcome on the data set of MNIST. So I believe many of you would have already worked with MNIST digit data set, images of 0, 1, 2, 3, 4 handwriting. And as you can see that all the pictures of one are kind of represented here using a same similar format, right? Which is you can say that I mean they're very much closer to each other in the latent space representation, right? So you can say these all are pictures of one, these all are pictures of two, like that. Sorry, these are, let's say these are pictures of 7, these are pictures of 9, right? And these are pictures of maybe 6 and 9 possibly, or something else, right? So this is how it sort of shows the so here we have color representation, I missed it, right? So these are the pictures of 1, green is for 0, like that. So you can see that this, I mean, it doesn't generate the graph like this, but it generates the values, and we can plot that on this kind of graph, a 2D latent space representation, right? And it shows different clusters of pictures, right? So every dot is a photograph, every dot is a picture. And so this is with a discrete autoencoder. If you want to do it with variational autoencoder, it would go like this, in which it will also show that how pictures vary from one space to another space. For example, this is 1, and this is a sort of picture of 2, but looks quite similar to 1, and this is a real 2. So it's going to show in a continuous space, which is going to capture the variation in the data happening up and how they are similar or different to each other. That also you can visualize with this help of variational autoencoders. Right, so autoencoders could be answer to your question when it comes to grouping observations, and yes, they show the gradient distribution of how the shapes are changing and how the shapes are similar or different than each other. In a discrete representation, it simply shows a group of pictures which could be similar to each other, right, in a discrete representation, whereas variational autoencoders show in a continuous representation of gradient, which represents the variation in the shapes. Right, that's an idea, everyone. Autoencoders are unsupervised learning, Amani, right? So they are unsupervised learning, but they are neural networks used for unsupervised machine learning applications. Okay, so I hope that answers all of your questions, everyone. We're good to move forward, right? So I hope we are all good with understanding of the problem statement that we are discussing. So main idea is that the problem statement, right? So are we all good with understanding of what is the problem statement we have? We have 202 pictures of dogs, 202 pictures of horses, and 202 pictures of humans. And what you want to achieve is we want to train a neural network which should be able to learn from this. And for any new photograph, it should be able to predict, whether that is a human or a horse or a dog, right? That's our objective. Are we all good, right? So I hope all of you understand at the moment that we don't have a lot of pictures. We have only 200 pictures, and which is where we have complex scenario, complex situation, different sizes, different aspect ratios, mixture of objects, and less amount of data. With this situation, it would be very difficult to achieve good performance on this particular problem statement. Though we should be able to achieve good performance with the help of transfer learning. So initially, we'll go ahead and try to develop a neural network from scratch, and we'll write every code from very scratch and try to see that how good can we go about achieving performance on this data set, right? So I hope we're all good with that moment and good to go ahead with this, right? Okay, so considering that we're good to go ahead, we'll go forward, and I'm going to open my Colab notebook. And take a new notebook over here. Okay, so I just need to get the data set. So as we're going to use in Colab, I will have to upload the data set over here. But for that, I will be using data set download from dataset download from GitHub, right? So let me open a new notebook. And here's the link, right? So the link to dataset, in fact, the whole command, right? I have pasted that in the chat box, right? So from here, you can get the same dataset in case you want, right? And I'm gonna name this as image classification using CNN, right? At the moment, let's say it's that way. Right, so wget is a Linux command which is used to download the data. So in the current directory of Google Colab, it will download this data from my GitHub repository. You can use the same link in case you want to download it later. And make sure that it's not only the link, it's along with the wget command as well, which is a Linux command. And as you can see that currently we don't have the data. So I'm going to run this and then I'm going to unzip this. Right, so now we could download the data. As you can see that we have image data.zip. So I'm going to unzip image underscore data.zip. Right, this is going to unzip the data set, and now we're going to get the data set unzipped over here, and done we are. And now you can see that there's also a folder with image data. Right, in this folder there's a data folder, and inside the data folder we have pictures of humans and dogs and horses. So you can see that these are the pictures of humans, right? A lot of pictures of humans and a lot of pictures of dogs and a lot of pictures of horses. The same data, we have just tried out accessing that in Colab, right? So yeah, that's the idea we have everyone over here. So I hope we have now understanding of what data are we talking about, right? And the understanding of the problem statement as well. Okay, so considering that we're good so far at the moment to with this part, we'll go ahead further. So what is objective? The objective is that we have three types of pictures: horses, humans, and dogs, and we have to train a neural network which can learn from this data. For any new picture, it should be able to predict whether that's a horse or a human or a dog. So our main folder, let's say our main folder where our data is, that is image data / data folder, right? So in this folder we have the data available. If I import the this is our main folder, and if I import few packages like OS for operating system, NumPy for mathematical computation, we may not need pandas, matplotlib for data visualization, right? So in MATLAB we don't have to load all of these packages. That's one of the benefit of that. All right, at the same time we're going to be also loading from TensorFlow .keras.utils. We're going to be importing two categorical, right? How did I unzip? So I use this command to unzip, which is unzip and the name of folder you can pass here, right? So this is the command I use to unzip. Right, from TensorFlow.keras, we're going to be also importing our .preprocessing. We're going to also be importing image, and from TensorFlow.keras. We're going to be importing models. We'll be using all of these, later, right? So later going further, we're going to be using this all. We're just importing them all together over here. So we have main folder, which is image data and data. If you look at the list of folders inside this, so I can say that list dir main folder, right? So let me save this in the variable names of folder. So we are trying to access how many folders are there into the data folder. So as we can see that we have three folders inside that. First folder is dogs, second folder is horses, and third is humans. These are the three folders that we have, in which we have lots and lots of images, right? So in dogs we have lots and lots of images. In horses we have 202 images like that, and in humans also we have that many images. What we have to do is we have to load all of these pictures and store inside a variable and create our data. So for supervised machine learning, which is like classification, you always need label data. So you need something called X, and which is a set of pictures, and you need Y, which is a set of corresponding label. So X should be what? A collection of all pictures. And Y should be what? Corresponding label to pictures in X. So whatever are the photographs in X, the corresponding label we have to keep that in Y, right? Then we will have label data as the first picture is dog, in Y also the first position says is dog. The second picture is dog, in Y also second position says is dog. 10th picture is horse, in Y also on 10th position it says it's horse, like that. So X is we have to create a set of pictures, and Y have to create a set of labels corresponding to those pictures. So how we go to the task here? The first task, everyone, is the data preparation, right? So what is the first task? The first task that we have is we need to create a data set. So in real application, when you work, you have to create a data set from scratch, right? So the first task is we need to do data set preparation. Once our data set is ready, we'll be able to program neural network, and we'll be able to go ahead and train that as well, right? So we have created X as an empty list, Y as an empty list. We need to load all the pictures, store inside X, corresponding label, store inside Y. I hope we are good with the task at the moment. Right, and we have main folder in which we have 3 folders. So we have to first go inside main folder, then go inside each folder, dogs, horses, and humans, and read each folder, capture all the images, read all the images, and store that into X. So this is what we'll be programming now, right? So we have to program that, go inside each folder, dog, horse, and human. From dog, read all the images and store in X. Corresponding label is Y. From horse, read all the images, store into X. Corresponding label in Y. From human also, read all the images, store into X, and corresponding label into Y. As we already have names, which is a list of folder names, so we'll say that for folder in names, right? That means for each and every folder in the names, we'll first get the file names, right? So file names. Instead of names, let me create folder names. It is much more interpretable or logical to say that. Folder names, right? So we have folder names. What are the folder names? Folder names are dogs, horses, and humans. So we're saying for each folder in the folder names, and these are just variables, right? If you're new to Python, don't get scared with them. All right, we'll say os.list_dir, list the complete directory as whatever the files are there. So we'll say list_dir main folder plus folder, right? So we'll get the list of all the photographs, right? Now this will be happening one by one for dog, horses, and humans. So currently, let's say it is for dog. So now we need to read all the pictures of dogs. So for that, we'll say for image file, or you can say for each image name in file names, we have to read that image. So first we'll say path. So path of that image would be what? First the main folder plus the folder which is dog or horses or human, plus I have to say slash, right, which is the path creation, and then image name. So this is how we get the path. Now once we have the path, we can read all the image, right? So we'll say image equals image dot. So we already imported image, you can see that, and this can be used to load all the images. So we have the function available with the image in Keras, load underscore image, and we can mention the path. We can also mention the target size as well. So what benefit of Keras is you can directly mention the target size, and it will read all the images and resize them into this particular size. So let's say my target size is I want to resize them into all 200 by 200, right? So this is a typical size I selected. So what this will do is it will read all images and convert that into 200 by 200, and so one by one it is going to do that. Currently our first image is an image variable. We have to convert this into array as well. So we have to say dot image to array img. Now once we have image available, what we'll do is we'll store that into X. So we'll do X dot append image. Now we have to store corresponding label into Y. So can we say that from whichever folder we are reading the data, the name of folder itself is the label? Do you agree with that? From whichever folder, currently if I'm reading data from dogs folder, so the name of folder can be thought of as label. If I'm reading data with horses folder, the name of folder can be thought of as label. If I'm reading data with humans folder, the name of folder can be thought of as the label, right? I hope all of you agree. So we can pass the name of folder itself as a Y, and we can have corresponding accordingly, the variables or the labels as the name of folder in Y. Other approach could be we can also pass the position of folder as well. So for 0 for dogs, 1 for horses, and 2 for humans, right? Let's do that. So we can pass position of folder. For that, we're gonna say 0 for horse, 0 for dog, 1 for horse, and 2 for humans. So we just have to say folder folder names dot index the current folder. So current folder's index, for example, 0 for dogs, 1 for human is, 1 for horse and 2 for human is going to be passed in this. Done we are, everyone, done we are. And now we have X and Y. We just need to convert them into array. So we'll say X is np.array of X. Y, we need to do one hot encoding for that, right? So we'll be converting into one hot encoded format, right? So one hot encoding, or let's say first convert into array and then later we'll do one hot encoding. So we'll say np.array of Y, and finally we can print x.shape and print y.shape. And we can see that here we have X as 606 images of each picture of shape 200 by 200 by 3. Last 3 represents what? It's a color image, right? The last value 3 represents it's a color image. That means every pixel has 3 values. If it were in black and white, we would not be having last 3, right? So let me know if you're good with this part, everyone. We can directly, yes, we can directly do that, Vinod. That's correct. Just I want to show that why, next step as a part, so that multiple steps do not get confused with that, right? So now we need to convert our label. So so from list itself, we can do directly convert into 2 categorical format, Vinod. So convert the labels to one hot encoded format. So we're saying that Y is equals 2 categorical, right? So we're going to be converting that into one hot encoded format of Y and print y.shape. So we converted that into one hot encoded format. So now we have label as 606 by 3. So whenever you're dealing with multi-class classification problem, you're going to be always using Softmax as an activation function, and you have to one hot encode your labels, right? So once you're done with that, convert it into categorical format, the labels. One of the other steps you can do is you can scale your data, scale the images. For that, you can say x equals, one of the simplest way to scale images is x equals x by 255. And next step is going to be to split data into train and test set. For that, we can say from sklearn dot model selection import train test split, and we can say x train comma x test comma y train comma y test equals train test split x comma y comma test size is, let's say, 0.25, 25% of data we want to use for testing, 75% of data we want to use for training. And we'll mention random state equals 5, or maybe any other integer we can pass here. And then we are everyone with that, and we have now the split data, right? So we have split our data into train and test set. So at this moment, we're done with the data set preparation. We have prepared our data and we have data ready for train and test set. We are good to go ahead and build the neural network and feed the data to the neural network so that we can train it. All right. Are we all good? Any question that you have everyone with the part of data set preparation? Feel free with that. Let me know about it. So any question you have with the part of data set preparation, let me know. Random set is to fix the randomness, right? So the train test split is going to happen randomly, right? So if I, it's like seeding the randomness, right? So if I run the whole code again and again, my train and test will change, right? So let's say if I make some changes in the data set and I run the whole code, I want to be sure that the change in performance is not because of the randomness, rather it is because of the tuning that I have done. And for that, I have to fix the randomness. So random state is to fix the randomness by help of seeding. I hope that answers the question. Right, let me know. The idea of random state is clear. If it's not, we can discuss it in more detail as well. Right. So it's seeding the randomness to fix the randomness so that every time we run the code, it should not use different approach for splitting that or different distribution for splitting that. It should use the same randomness. That's the idea. Can you explain the for loop? Yeah. So you see what we have done is we have the main folder, and inside main folder we try to list all the folders. So inside folder names, inside the variable folder names, we have 3 folder names: dog, horses, and humans, right? And you can see that here is our data, right? So we have data folder. Under that we have humans, dog, and horses, right? So we want to go inside each folder and load all the pictures. So we have 3 folders: dog, horses, and humans. What we have done is we have started with a for loop for folder in folder names. That means this for loop will iterate 3 times, first for dogs, then for horses, and then for humans. Now at a time, whenever it is for dog, we are trying to read all the pictures, the name of all the pictures. We're trying to load the name of all pictures using this line, right? So this is where you're doing what? Loading the names of all pictures, right? So we are not loading the pictures, we are just loading the name of pictures, right? So once you loaded the name of pictures, then iterating through those pictures, right? Then what we're going to do is running the for loop to iterate through each picture name, right? So we want to iterate through each picture name. So for each image name in the file name, we are accessing the path. We are creating the path of it, trying to load the image, make sure that it is of 200 by 200, because as we know that all our pictures are of different size. Convert that to array, right? Because by default it loads as an image object data, image object format. So we have to convert that to array and store inside X. Now X is the picture, right? X is going to be collection of pictures. We want Y to be a corresponding label, right? So in that case, we have passed the index, right? Index in the sense dog is on 0th position, so 0 for dog. Horse is in 1st position, so 1 for horse and 2 for humans, like that. So we're passing the index of the folder name inside Y. So Y will be having 0, 1, 2, 0 for all the dog pictures, and 1 for all the horse pictures, and 2 for all the human picture, right? So that's the idea for loop. Are we good with that? Right, Kalyan, I hope you're good. The understanding of for loop, right? Now there's a question. One hot encoder. So I'm going to explain that. Let me take if we have any other question related to the for loop. Is data preparation same for? Yeah, almost same. They are also shorter way, Humera, right? So there is a very shorter way with TensorFlow, which is called image data generator, right? Because in this case, we are loading all the pictures, right? Let's say if you have 50,000 pictures, you may not want to load all the 50,000 pictures at once in your RAM, right? That's where you have image data generator. What image data generator does is you can specify a batch size. So what it will do is it will load, let's say you specify a batch size of 100. So it will load at a time 100 pictures from your machine, do the manipulation and train the model. Then load another 100 pictures in a batch. So it will try to read pictures in a batch. So at a time in your RAM, only 100 pictures will be there, but it will train the model for all the 50,000 pictures. So we call it image data generator. That is a more smarter way, but more recommended for a situation where you have very large volume of data, right? As in this case, I want to show you clear picture, so I took this approach, but this approach will not be right if you have large volume of data, because if I have 50,000 pictures, I unnecessarily do not want to consume my RAM and keep all of them in my RAM at the moment while training the data. So at the moment when we have loaded this, you can say all these 600 pictures are in the RAM. As the 600 pictures are small volume, if they are in the RAM, it's fine. Right. So image data generator is also very popular approach for loading data, and you can load data in batches and train the model as well. Right. So yeah, I would recommend you to explore that approach as well. Right. It's available with Keras and a very simple and clean code it requires. Okay, so that's the answer to your question. So Tushar, I'm going to take the example of one hot encoder for sure. Don't worry about that. Right, Johi as well. One hot encoder I'm going to discuss. Just I want to make sure that the questions related to the current cell of for loop is clear. Size of image in hyperparameter, will it influence classification? Yes, it would definitely, Vinod. So you are make sure that your size is sufficient so that it includes all the shapes very properly visible, and it is not distorting the pictures as well. You cannot go for very small size because that would impact on the quality of pictures. A very large size picture will also make your data go very slow, and at the same time it will increase the number of hyperparameters and make your model more bulky. Right, so you have to, like, generally 200 to 300 and 400. These are very standard picture size that people take while training neural networks. Right. So yeah, that's the idea. Should we remove confusing images? Yes, that can be done, but at the same time, you'll make, Abhishek, your neural network a bit weaker, as it will only be able to give you good performance in a good images, right? So if you remove confusing images, your neural network will become less generalized. It will become weak because it will only require clean images to make prediction, right? And you don't want your neural network to be dependent on only clean images. Otherwise, it is of no use, right? It's like your neural network works in daytime but doesn't work in nighttime, right? That kind of situation may occur. Sarah, the idea of X in for loop, right? So I hope that's a question you're asking, right? So X is an empty list we created. We are loading all the images and we are appending all the images inside X, right? So each picture one by one will be stored inside X, like that. That's happening, right? So for each folder, each picture will be stored inside X. Is that answering your question, Sarah? Let me know if you have any question. I hope this answers your question. Right, let me know if it is not, in case you have any other question. Right, then the question is about one hot encoding, right? So let's talk about that. So one hot encoding is what? Whenever you have label, right, you're going to be sort of, you have to do one hot encoding of the label if it is multi-class classification problem. Now, why do I need that? So yesterday, if you remember, we discussed in a neural network, the number of input neurons in a neural network in the input layer depend on number of features, and the number of neurons on the output layer depend on number of classes. So if we have a 3-class classification problem, how many neurons we will need on the output layer, right? So you can say for a 3-class classification problem on the output layer of the neural network, we will need 3 neurons. I hope all of you agree on that, right? Now that means the neural network will make 3 predictions, right? It will predict 3 values. So when you have 3 neurons on the output layer of neural network, why? Let me repeat again. We have a 3-class classification problem, because that means for every picture, we have to classify that either it is a dog or human or horse, right? So there are 3 types of objects we have: dog, human, and horse. Let's say if you also have a cat, it will become 4-class classification problem. If you also have a car, it will become 5-class classification problem, right? So we have currently 3-class: dog, horse, and human. That means on the output layer of the neural network, you need 3 neurons. So 3 neurons will predict 3 probabilities. What are the chances of this picture becoming a dog? What are the probability of horse and probability of human, like that? Now 3 neurons will make 3 predictions, or you can say we will have 3 values. Now when the neural network has made prediction, you have to calculate error. Now when it comes to calculating error, right, so let me draw it here to just explain it better, right? So currently what's the situation? You see, the situation is that on the output layer, you'll have 3 neurons, 1, 2, and 3, which will predict 3 values, maybe 0.2, 0.6, and 0.2. These are the probabilities you may get from 3 neurons. on the output layer of the neural network, right? Now, in order to compare this, right, in order to calculate error associated with this so that you can update the weights, you need 3 values, right? So these are the 3 values of y hat or y pred. You need the 3 values of the label to be able to calculate error, right? So your label should be converted into 3 values, right? So currently our label is what? If the image is of dog, the label contains 0. If the image is of horse, the label contains 1. If the image is of human, it contains 2, 0, 1, 2. So our picture might be, first picture is dog, second is also dog, then horse, and then a human, dog, human, dog, horse, and human, like that we have. These are the pictures or labels might be having. So one hot encoding is what? One hot encoding is what? It converts these pictures into 3 columns, right? So what it will do is it will convert this picture. Whenever it is 0, it will say 1, 0, 0. That means yes, dog, no horse, and no human, right? For this also 1, 0, 0. For 1, it will get converted to 0, 1, 0. That means no dog, yes horse, no human. This will get converted to 0, 0, 1, 0, 0, 1, 0, 0, 1. 0 will get converted to 1, 0, 0. 1 will get converted to 0, 1, 0, 0, 0, 1. This is what we call one hot encoding, right? So in one hot encoding, you try to convert the label into as many as classes as you have. So once you have 3 labels, now you can compare that with the 3 predicted values, right? So why do we need one hot encoding? So that we can calculate error, right? Because on prediction we'll have n values if n class classification problem is, and to be able to do that, you convert your labels into one hot encoded format. Yeah, only for the label. Only for the label you have to do one hot encoding, Rahul. That's y variable, right? So this is your y variable. The pictures are x and the label is y. Are we good with that? Tushar, let me know if you're good so far with the idea of one hot encoding. Those who have asked the questions related to Juhi, I hope we are good with the idea of one hot encoding, right? I hope you all are good, everyone. Great. Considering we're good so far, let's move forward, right? So this is where we have done one hot encoding of the label. So you can see that we have only done it for y, which is our labels. All right. So let's go further. This is where we are done with the idea of data set preparation. Now it's time that we're going to be going ahead and building the neural network. So we're going to be shifting to the modeling part, where we will be using the approach which is convolutional neural network. Okay, so that's what we how to do modeling of convolution neural network. Let's start with that with the help of TensorFlow Keras. Right. So we can say that we can start with a sequential model. You can think of a sequential model by default as an empty neural network. There's a question, how much percentage of data set we should use take for testing? Generally, it is 20, 25 to 30, right? This is the standard range we take. So we usually split it into 70, 30 or 75, 25 or 80, 20. If the volume of data is very large, you want to go for 80, 20 or maybe 90, 10 as well. Let's say if I have 1 million pictures, I can even take maybe 100,000 pictures for testing, which is enough, right? So I want to go for 90, 10. But if I have only 50,000 pictures, I may want to go for, let's say, 85, 15. If I have only, so let's say the picture size, higher the test size increases, because in test, you may want to keep variations to be able to test the model thoroughly, right? So lowest size that we go for 70, 30. We should technically do not go less than 70, 30. Otherwise, the trained data size will be not sufficient to train the model. Right. Okay, so that's an idea about the train and test split, right? Higher, very high the volume of data, very less the test size you want to keep, because in less percentage of this data size, you can also have good amount of variation if the volume of data is big. So here we go, everyone. We're going to be starting out with the sequential model and saying that model equals models dot sequential. Right. Random state is fixed. Balkrishnan, the value of random state you can use 5, 6, 7, any integer you can use as the value of random state. It's up to us what value do we want to use, as a part of it. 80, 20. It's optimal. Yeah, I mean, it's a good ratio, I would say, right? So let's start with that. Here we start with sequential model. Sequential model is an empty neural network, right? And now we can add layers to this particular model, right? So add the first convolutional layer, right? Whenever you add a first convolution layer or first layer of with the first layer of sequential, right? Or else, a better approach could be, instead of convolution layer, we're going to just add, let's say, add an input layer. We're going to add an input layer first, right? And just input layers are not computational layers, right? So they are simply input layers are non-computational layers. So we can say that model dot add layers dot input, right? So input layer is never a computational layer. And here just we mentioned the idea of shape of data. So shape of our data is what? 200 by 200 by 3. That's that. So input layer do not perform any computation on data. Model dot add. Now we can add the first convolution layer. So layers dot conv2d, and we're gonna mention filters. So number of filters is you should always start with lower number of filters and increase that to higher number of filters, right? So let's say I start with 10 filters. And kernel size stands for filter size. So kernel size is going to be, let's say we start with 3 by 3, or maybe we can also start with 5 by 5 as well. And finally, we can mention here activation, that is ReLU. So in this step, we have implemented convolution and ReLU together, right? So that's where we're done with the part. Now we can add a max pooling step, right? So let's do that as well. So we can say model dot add layers dot max pooling, right? So add a max pooling layer, max pooling 2D, and we can mention the pool size as 2 by 2 window. So this is the first step that we added here, and you can say that 1 unit of feature detection we have done here. 1 unit of feature detection. Okay. If I want to increase it further, let's say I want to get a good model over here, we can kind of add 1 more unit of feature detection. Just copy this out and paste it, right? And we can make some changes, as in we want to have, let's say, 20 filters here, and the size of filters we want it to be 3 by 3, right? Again, add convolution pooling like that. So we can add as many as convolution pooling layer, that means feature detection layer over here, and try to train the model accordingly, right? So that's one of the approach. Post that. Now we have to shift. So this is how we can program the feature detection segment. Now from this, we have to shift from here to classification segment, right? So you can say that here, this segment is more of feature detection segment, right? So this is the feature detection segment that we have programmed here, right? Next thing that we need to program is the classification segment. So we're done with the end of feature detection segment, and we need to program the classification segment of the same neural network, right? But whenever you have to shift from feature detection to classification, yes, that's correct, Gaurav. So convolution and ReLU both all together. We can add separate line of code as well, but yeah, we are doing it together. No, filter is the filter. The process of convolution will generate the feature map. So the output of convolution will be feature map, right? If you remember yesterday's drawing, which is this one, let's say. So this is your image, and this is the filter. And the output of convolution, when the filter is applied on the image, the output will be the feature map. No, filter is same as kernel. Filter is, here the nomenclature is different. So, in this case, the filter is same as what do you mean by kernel? Okay. That's one point. And there's another question, can we have non-sequential model? Yes, we can have a standard cascade model as well, in which we can keep on adding more and more layers manually, right? So non-sequential model as well. Sequential is just an approach for programming it, right? So the actual algorithm is convolution neural network. Sequential is a programming approach, which is part of TensorFlow.Keras, right? And these are the programming approach as well, which could be non-sequential programming approach. All right, and that's one idea. So we are going one step in 2 line of code. That was answered. We know that I hope we're good with that. right? So filter is not same as feature map, but filter and kernel are same things, right? And yeah, so in the first convolution layer, we took 10 filters, right? So the number of filters and the size of filters are hyperparameters. That means it's up to us how many filters that we want, and what is the size of filter that you want, right? So that's more of idea, right? So it's an hyperparameter. We have to decide that, okay, you want to have 10 or 20 filters. It's an arbitrary value, and it may not be suitable value. If I see that there's a bad performance, I may want to kind of change this value as well, right? So Gaurav, I hope you're good with that. The number of filters are hyperparameters. So there are 10 filters. Each filter is of shape 5 by 5. In this layer, there are 20 filters. Each filter is of shape 3 by 3, like that. Are we good with that logic? Gaurav, I hope, are we good? Vinod, I hope we are good. Let me know. Any question you have. Input layer. So what is input layer? Input layer is actually, we're defining what is the shape of data that the neural network will be expecting, right? So input layer is just representing the shape of data, right? As you remember, we discussed yesterday, in a neural network, input layer neurons do not perform any computation. They just represent the features of the data, right? So we just added input layer, and which will not do any mathematics on it. It will just represent that, okay, our images which will be feeding to this neural network will be of shape 200 by 200 by 3. Because we have reshaped all our images. If you remember, we have reshaped all our images to this particular shape, right? So it will be by default using this value of 200 by 200 by 3. I mean, yeah, our images, all of our images are this shape. So we have to mention that, not by default. We have to mention that this is the shape of our images. And when we will train you, we'll feed these images of this particular shape, right? So are we good with that, Joey? Right? So we have our all images were of different size. So 200 by 200, we have resized them. As it is color image, it would be 200 by 200 by 3. So the 3 represents it's a color image. So this is the shape of our data, which is what we're mentioning here. Input shape is 200 by 200 by 3. Are we good with that, Joey? I hope that answers the question. There's a question, what did you choose for stride and padding, right? So Amani, I didn't choose any value. There's a default value. So by default, it uses stride of 1 and padding of 1, right? So that's a default selection, which we can change as well, right? So you can see that here, there's a option for strides. Right, so there's an option for strides, and so it's not showing up. It should pop up. Strides. So there's a default value of stride 1, right? So stride is 1, padding is 1 by default. Okay, so I didn't choose that. In Keras, TensorFlow.Keras, it doesn't allow you to choose a specific value for padding. Rather, you have to choose same or valid, right? So by default, it's the same padding. We can choose valid padding. In valid, it will try to adjust the data, the number of layers for padding, so that the output shape of feature map is same as image. So yeah, there's a default value. Activation ReLU, how will it understand it has to use ReLU algorithm? It is predefined, Justin. So internally, ReLU is a keyword inside TensorFlow.Keras, and whenever you mention activation as ReLU, it will use the corresponding mathematical function, right? So it's predefined here. We don't have to write the mathematics behind ReLU. We can just mention the keyword. It will identify internally, right? So that's a that's a very much benefit of TensorFlow as a high-level API. Right, so that's the reason TensorFlow is a very popular API, or you can say programming interface to program deep neural networks and deep learning algorithms. Can you imagine filters as neurons in the hidden layer? No, filters are weights of the hidden layer, Vinod, right? So the filters are the weights of the hidden layer, right? And yeah. So yeah, that's more of idea. We should not think of them as the values of filters are weights, and you can say that count of filters can be thought of as neurons. One way, Vinod, right? The count of filters could be thought of as neurons, and the values of filters are weights. So technically, filters are weights itself, but you can think of them as the count as neurons. That many neurons are there, or that many layer of it. Computation is going to be happening, but those neurons are not same as the neurons doing weighted sum activation function, right? So that's where we do not technically call them neurons generally, right? So yeah, that's my idea. And this question, can you please share the practice details in PDF to our mail? I would be asking the team to share email with the list of all the documents. I mean, the code files that you have done today and yesterday. and the PPT as well, right? So that we'll be sharing to all on the email for sure. Videos will be uploaded on YouTube, and you will be also receiving the links of videos of yesterday and today's session as well. There's a question, convolutional layer is acting as hidden layer here. Yeah, you can say that, Juhi, but that's mostly the feature detection segments. In feature detection segment, we do not call them hidden layer. Mostly we call them hidden layer in the classification segment, right? So in classification segment, the input internal layers are called as hidden layers. And here we call them convolution or pooling layers, and they are mostly feature detection layers, right? So it's just a difference of nomenclature, how do you call them. So Amani, yes, we'll be sharing the files, the PPT and the code files over email, along with the link of YouTube video as well. It may take mostly by tomorrow, you should be receiving that. Can you please tell what is the purpose of max pooling? Rahul, at each layer of convolution, you may want to do max pooling, but may not be necessary. So max pooling simply does what? It does the downsampling, so that if your data is large, you may want to do, I mean, if your image size is large, let's say 500 by 500, you may want to do max pooling 3 to 4 times as well, right? So each unit of convolution and max pooling constitutes one feature detection unit, but it's not necessary that to use every time you use convolution, you use max pooling. You can also use at the end as well, right? So let's say if I use 5-6 convolution layers, I can use 2 to 3 max pooling layers like that. There's no specific rule that every convolution layer should have or should not have max pooling. You can have it. If you think that's going to help you to do better feature detection, you can put that out. That's one question. I hope Julia answered the question. Convolution layers are technically, we do not call them with the name hidden layers, right? Because they are used for feature detection, and mostly the word hidden layer is used in the classification segment to represent the neurons or layers of neurons which do weighted sum activation function, right? That's important point, right? And one convolution is one unit of feature detection. You may want to use multiple convolution because each convolution layer does some level of feature detection. So when you use multiple convolution layers, initial convolution layers are going to do low level feature detection. That means they're going to identify the features like edges. The next convolution layers are going to do high level feature detection, as they're going to identify multiple high level features. For example, like this, if you see this example, so this is convolution, and the first convolution from the face is identifying the boundaries or edges. Another convolution relevant pooling is going to identify the features like eyes, ears, and nose. Another convolution relevant pooling is going to identify even high level features like the face structures, right? Similarly, here you see this is the first convolution relevant pooling. It's going to identify, this is the first one which is going to identify low level features like edges and boundaries, right? And next convolution layer is going to identify a bit high level features like circles and lines. So first convolution layer may not be necessary to may not be sufficient to help you improve the performance of your model, right? You may want to go for multiple such layers, right? That's an idea. In something like biomedical signals, we want to do classification of signals sometimes, and we don't have large data set to train the model. Yes, that's very much correct, Fatma. And we're going to be see a solution to that as a part of transfer learning, which is very important. So I believe that the next step which you're going to talk about transfer learning is going to be very helpful to you, and to handle such situations, right? For that reason itself, I took a small data set to explain the concept of transfer learning and to bring to that particular level. So that's the idea, everyone. There's a question, please share the hands-on file, Python file at the end of the session, so that we'll be able to exercise at some more databases. Sure, we would be sharing all these files over email, right? Is it useful for brain tumor? Yeah, it could be definitely useful for brain tumor. You can, in case you want to detect that, you can use k-means or c-means clustering. If you want to do classification, you can use this like segmentation. You can use neural network for the same. 200 by 200 by 3 is the shape of image, right? If you remember, all our pictures are of different shape, and all of our pictures are of different shape, right? And what we did is, while loading data, we reshaped all our pictures to 200 by 200. So we thought that, okay, let's take 200 size. Let's say first picture is of 500 by 600. Second picture is 300 rows and 700 columns, like that. So every photograph or every picture is of different shape. To proceed ahead, we need to reshape or resize them to the same shape or to the same size. So we fixed the size 200 by 200. So we loaded all our pictures to this size 200 by 200, right? So the shape of X became 200 by 200 by 3. That is, each picture is of 200 rows, 200 columns, and 3 means it's a color picture. That means every pixel has 3 values. So 200 by 200 by 3 is the shape of image. 3 is RGB. Yes, that's correct. Right. So this is the shape of our data. That's the reason while building the neural network, we mentioned the shape of data is 200 by 200 by 3. So that's the idea. Let's go forward, everyone. And now, so once we're done with the feature detection segment, now we need to go to classification segment. But in order to shift, we have to always add a flatten layer. So flatten layer will do what? It will convert the matrix into array format. So if I have 5 by 5 matrix, it will convert into 1 by 25. Because classification segment always expects a matrix, and feature detection segment process data in the form of, classification segments always expects an array, whereas feature detection segment is going to process data in the form of matrix. So now we're going to go ahead and in the classification segment add the first hidden layer. We're going to say model.add layers.dense. So dense layers are the layers which do weighted sum activation function, right? So that stuff you do here. And let's say we can add a layer with maybe 150 neurons with activation again as ReLU. Finally, let's say that add the output layer. We can add even more hidden layers as well. So model.add as output layers also perform the same mathematics weighted sum activation function. We'll use dense layer for that. But in output layer, how many neurons should we keep here, everyone? How many neurons should we use in output layer? So I hope all of you agree that we should use 3 neurons, and activation should be for the output layer. As it is multi-class classification problem, it would be Softmax activation function. For 2-class Sigmoid, for multi-class Softmax, for regression, you can use ReLU or identity activation function. Okay, so here we are. At the moment, our neural network is ready. We are good to go ahead with this, right? 150 is an hyperparameter. It's just a hyperparameter. You know, number of neurons you want in hidden layer is a hyperparameter. We have to decide that. I just took an arbitrary value. Okay, so I got an error here. So I don't have flatten. Oh, I am making some typo error in the flatten. So it should be flatten. All right, done with that. So good to go ahead, and we have our neural network ready, right? If you want to see the neural network, you can also do here something like plot_model of the model. It will show you the graph of the model. How does it looks like in a structured format? So as you can see that this is our neural network, right? In which we have the input layer, which is going to accept input, and then it's going to feed to the convolution, max pooling, convolution, max pooling, flatten, dense, and finally dense. This is the architecture of our neural network, right? And the importance of flatten is what? Generally, the feature detection segment is going to process data in the matrix format, right? But the classification segment, which is dense layer, they always need data in the vector format or array format. Flatten simply converts or resizes data from matrix to vector, right? So you can say that it converts, if I pass 5 by 5 to flatten, it is going to convert that to 1 by 25, right? If I had to show you a bit more clear way, I can do here model.summary, and this will show the summary. So you can see these are different layers. Just before flatten, we have 48 by 48 by 20. This is the output of max pooling. The shape of data with max pooling is 48 by 48 by 20. So flatten is going to do what? It's going to multiply 48, multiply 48, multiply 20. Is going to convert data into 1 by 406080, like that. 46080. So it is converting this. There were 20 matrices of 48 rows and 48 columns. There are 20 matrices of 48 rows and 48 columns, which is converted into 46080. Like array of, or a vector of size 46080, like that. That's what flatten does, right? And yeah, that's an idea so far, everyone. So let's go further about this. We're going to be compiling the model. So model.compile. Dense is a type of layer where each neuron does weighted sum activation function, right? So the standard classification neural network, does weighted sum activation function, 2-step, x1w1, x2w2, x3w3 plus b is weighted sum. F of that is activation function. So all the neurons of dense layer do this job of weighted sum activation function, like that. So whenever you have classification segment, there we always use dense layers. And why do we call them dense? Because they are fully connected. Each neuron of layer 1 is connected to each neuron of next layer. So we call them dense layers, right? So here we go, and So we're going to be now compiling the neural network optimizer Adam, because Adam is a modification to gradient descent. I hope all of you know gradient descent, which is the approach widely used for optimization of neural network and uploading the weights and bias of the neural network, right? And then we have loss of that is the cost function, categorical cost entropy, and metrics. That means how do you want to assess the performance of model? So we want to always check the accuracy of the model. So we want to assess the performance in the form of accuracy. And finally, we will train the model, model.fit. We'll train the model with X-train and Y-train, which is our training data, which we created. Epochs, that means number of iterations, we want to go for 10. And batch size, that means how many images that you want to feed at once. So let's say we want to feed at once somewhere around maybe 100 images. And similarly, we can mention validation data as X test, comma Y test. Right, anything else they are missing? I don't think so. We can good to go ahead and train the model. Oh, I have to mention here white test, not white test. So at the moment, we're going to go ahead and train the model, and you can see that it started with the first epoch. Going to go for maybe few iterations in the first epoch, 5 iterations, because we have total 600 data, right? 600 images. Out of that, in train, there must be only 500 images are in the train data, right? So somewhere around that. So for that reason, we are training the model here, and in the very first epoch, the accuracy on train data. So accuracy shows accuracy on train data, whereas val accuracy shows the accuracy on test data. So the val accuracy shows the accuracy on test data. As you can see, that accuracy on train data is 32%, which is very bad. And test data accuracy is also 33%, which is very bad at the moment. Right, so that's the idea. There's a question, can you explain output size of convolution? Yes, I can do that, Gaurav. Just let's finish this training and then we can do that. There's a question for 2-class classification. What will be the impact of using softmax activation instead of sigmoid? Usha, it's just, you know, if for 2-class you have both the options. If you use sigmoid, you don't have to one-hot encode your labels. If you use softmax, you will have to one-hot encode your labels. Right, that's the main difference. Otherwise, you will get almost same kind of performance with both. It just Softmax is going to be a computationally more expensive compared to Sigmoid. Right, so computationally, Softmax is going to take on large volume of data. It's going to make your process a little slower. Sigmoid is going to keep it a bit faster. Okay. Other than Google Colab, bigger data sets can be used. You can use on Kaggle kernels as well, which are also powerful and popular. Categorical cross entropy. Yep, sure. Didn't understand the compile statement. All right. So optimizer Adam. Optimizer is the the method that you don't use to train the neural network. That means update the weights and bias of the neural network. And in this case, we're using Adam, which is you can think of it as adaptive gradient descent, right? It's a modification to gradient descent. And the benefit of using this modification is that you don't have to mention the learning rate. Right, it takes automated value of learning rate and tunes that automatically using momentum, and we don't have to specifically mention a single value of learning rate. That's the benefit of optimizer Adam. Loss is the cost function, right? So for anything, you have a cost function associated. For every process, you have a cost function associated, right? So if you're using softmax activation function, the cost function is categorical cross entropy. There's a mathematical formula behind the cost function as well, right, which we'll discuss now in just a moment. So at the moment, when we train the neural network over here, you can see everyone that we have 92% accuracy on trained data, which is very good. But on test data, we just have 65% accuracy, which is very bad. That means our model is heavily overfitting, right? Our accuracy on trained data is very high, 92%, whereas on test data is 65% only. That's a very bad model, right? And it's very heavily overfitting. Okay, so we don't have a good model at the moment, and we have to tune this further to improve the performance of this. All right, are we good with the idea here, everyone? The accuracy on trained data is quite high and test is quite low, so that's called as overfitting model, and which is not a good model, right? It should be having good performance on train as well as good performance on test as well, right? So we didn't get that. We can also do a bit of tuning, go ahead and add more layers, remove more layers, do more of optimization, use regularization, and try to improve the performance, right? So whenever it is overfitting, you can use regularization, or you can use dropout optimization to control overfitting. Okay, So I hope you're good with that part. So let me know if you have any questions related to the performance. Then I have to answer a few of the questions which is related to the convolution process and the understanding of categorical cross entropy, right? So are we good so far with this part, everyone? I may not be able to help you immediately. Can you copy and paste the code, or maybe can I copy and paste the code in my model, right? Maybe that should help you, right? So this is the model, and I'm going to copy and paste this code in the chat box, right? So if you're doing it right now, this is something that should be helping out. And as well, the code for compilation and training, right? So these two codes should be helping you to sort of keep it active. All right, so now let me answer the question. Can you explain the implementation of cross-validation in some example instead of hold one out approach we are implementing? Instead of the hold one approach. Yeah, hold one out approach. Yeah, I can explain that, but no, in the current session we don't have. I think it's going to be very difficult to accommodate that, Vinod, right? So maybe in upcoming webinars, there are going to be a lot of upcoming webinars. I can accommodate that. At the moment, we have a lot of topics to cover going further. So I'm really sorry for that. All right. So, but yeah, we will have a lot of exciting topics. So you're going to love them for sure. Okay. So let me explain a quick idea of what is categorical cross entropy and what is that, how is this particular thing is calculated over here. So first thing, categorical cross entropy. All right. And so you see, if you have learned any part of machine learning, at least linear regression, you would know that there is something called cost function, which is called error function. All right. And which is, how we represent error. So, so whenever you use, let's say for linear regression, or the error function is MSE, and the formula for error is j equals 1 by n or 2n, summation of I equal to n y minus y hat square. We call it MSE, mean squared error. And if you use activation as, if you use activation function in case of neural network, if you use activation as ReLU, or you're using identity, this is your error representation. This could be one of the way to represent error in such situation, right? So okay. Similarly, if it is a classification problem and you're using activation as sigmoid, then the cost function becomes, right? So the loss or cost function becomes, the loss function becomes binary cross entropy the formula is j equals minus 1 by n, summation of I equal to 1 to n, y of log y hat plus 1 minus y of log 1 minus y hat. Whenever you use activation as Softmax, the cost function becomes categorical cross entropy. So we call it technically categorical cross entropy. So whenever you call categorical cross entropy, it's going to take this formula to calculate error, right? So this cost is just to calculate error. How to calculate error, right? So summation of I equals to 1 to n, y of log y hat, right? So this is the formula for categorical cross entropy. So according to the type of problem you're solving and the type of activation function you're using on the output layer, the formulation for cost function will change, right? So if I use ReLU or identity, it will be MSE or MAE. I can also use sigmoid, it will be binary cross entropy, and the formula will be y of log y hat plus 1 minus y of log 1 minus y hat, summation of that with 1 minus 1 by n, and categorical cross entropy minus 1 by n, summation of I equal to n, y of I log y hat, right? So this is how, so whenever we mention binary cross entropy or categorical cross entropy, it internally takes this particular formula to compute the loss or the error, you can say in general, right? So that's the idea. So there's a mathematical formulation behind, mathematical formulation behind this categorical cross entropy, which is used to calculate, which is used for how to calculate error associated with prediction. And that's the error that neural network tries to reduce in every iteration when we train it. Okay. So yeah, that's the idea, everyone. I hope we are good with that particular approach. And another idea is, there was a question about elaborate. So I hope we are good with that, Humaira, right? The understanding of categorical cross entropy. This answers your question a bit, right? And so categorical cross entropy is representing the cost function or the error function, and yeah, the error function, and there's a specific formula to that. All right, next another question was to explain a bit about from Gaurav. It was convolution layer size, right? So first thing, this is the output shape of the model, right? So this is simply the output shape of the model, all right? And these are the number of parameters, that is the number of weights and bias over here. So as we used 10 filters of shape 5 by 5, so you can say 5 by 5 is 250, and 10 is the number of filters. So that is going to be, you can say, did we use 5 by 5 over here, or we used more than that? Possibly, I'm not sure with that. All right, so I guess we used 5 by 5 and 10. So 5 by 5 is 25, and 10 is 250, and then why is it getting actually more of 760? It should not be according to mathematical calculation over here. Did we use 10 kernels of shape 5 by 5? So 5 5s are 25 kernel size, and that's going to be 250. So it's going to be 250 and 260 technically, all right? And it's getting 760, which is where I need to check out why is that happening. Okay, so yeah, 760 simply represents the number of weights and bias, that is the number of parameters, which is going to be calculated based on the filters. Now, next is going to be the idea of, but yeah, it's going to be color images as well, right? So 250, okay, 250 into 3, because it's color image. So 250 into 3 is going to be 750 plus 10 bias, 760, right? So we have 760, and then 196 by 196 by 10. This is the output shape of the feature map, right? So when you apply a filter, where is it? Yeah, when you apply a filter on an image, and this is the image, and you apply filter, and the output is feature map. So how is the size of feature map calculated, right? So the size of feature map, the formula for that is FM size is I image size, you can say, or I should say, let's say K minus 2 into P upon S. If K is the size of image, right? So if K is the size of image, K is the size of image, 2 into padding divided by strides. That's the idea. So let's say in this case, I'm not using padding, right? And I'm using more of a stride, right? And so it's going to be K, that is original shape of image, which is, let's say in this case, 1 2 3 4 5 6. So 6 into 0, 2 into 0 divided by stride of 1, which is going to be 6, right? So the output says shape is going to be more of, you can say, 6 like that. I hope I'm not wrong here. Yeah. Similarly, in our case, we're using 200 by 200, right? So 200 minus 2 by, you can say that it's using a padding of 2, right? So 2 into 2 by 1, which is going to be 196, right? So whenever, so the default padding is not 1 here, default padding is 2 here, right? So the formula, if you apply 200 minus, which is the size of image, minus 2 into padding divided by stride, that's the formula to calculate this 196 curve, right? So the size of image minus 2 into padding divided by stride. So there should be the padding of 2. So 2 into 2 by 2 into 2 becomes, you can say, 4. So 200 minus 4 divided by 1, it's 196. Similarly, you see here it is 98. Okay, and but why is that? It's becoming 98 here, right? And yeah, so 98 minus 2 into 2 again. So it's not, should not use a different level of it, right? So you're getting 98 from 98 to 96, right? Which is a challenge. Okay. And we are doing here filtering, I mean convolution with the filtering of 220. That's fine. Okay. Actually, yeah, the filter size, which is fine. I need to check with this part, you know, the formula is not fitting up here. I mean, it's fitting up for maybe padding of 2 for the first convolution. Okay, for 5 by 5, it must be taking padding of 2, and for 3 by 3, it's taking padding of 1. Okay, So that's that's also one of the things here. For 5 by 5 it must be taking padding of 2, and for 3 by 3 it's taking padding of 1. So the formula remains same. That's the formula of the image size minus 2 into padding divided by the stride. Using that, this is calculated. So as we used 5 by 5, it was taking padding of 2. For 3 by 3, it's taking padding of 1. Right. So for 3 by 3 padding of 1, 5 by 5 padding of 2, 7 by 7 it will take padding of 3, like that. It will increase according to the size of filter. So yes, the formula remains same. K minus 2 by 2 into padding divided by the strides. That's the formula to calculate output size of feature map. I hope we could do that, Gaurav. Right, so that's how these values can be calculated further. Max pooling is going to just make it half. So 1 by 2 of 96 is going to be 98. Similarly, 1 by 2 of 96 is going to be 48. So max pooling just makes it half, as it does the downsampling by 2. Okay, so that's the idea. If you don't, others, if you have any question in this, like, at the moment we cannot spend a lot of time on this, but because we have to proceed further. But yeah, this is where you can get into a bit of more idea about convolution and understand the size calculation. How is it calculated? Can we improve the testing accuracy? Yes, we can do that. That's where we have to improve the performance, right? So what we can try to do is we can try to make some changes in the performance of the the number of layers over here, right? So maybe what I can do is I can add one more convolution layer, right? So add a convolution layer. So I can add one more convolution layer here. So add a convolution layer with, let's say this time, filters of 30 of size 3 by 3, and here we added filters of 40. So now we have convolution, and then pooling, convolution, and one more convolution. Let's say I'm going to add so 10, and I'm going to make it 20 actually, right? And this one, so 2 convolution pooling, 2 convolution pooling. Now we are using this architecture, right? And this is where I'm going to make it 30, right? So 2 convolution pooling, 2 convolution pooling, right? So and this size I'm going to make it 5 by 5. We can have 3 by 3 as well, not a challenge, right? So now I try to improve the architecture of the model. 2 convolution pooling, 2 convolution pooling, and then flatten dense, right? Let's see if this helps in doing giving better performance to us. So now the structure of model we have is what? Input layer. We have the input layer, convolution layer, and pooling layer. Again, convolution, and pooling. Flatten dense. So we can optimize the architecture model according to how we can module it to get the performance out of it, right? Again, it should not be a random and blind optimization. We have to always take good intuitions and decisions, and also verify on what grounds are we taking to increase that. So we're expecting that this should help to improve the performance of model. Let's see that if it does help or not. Right. There's another question. Can you give any briefing about confusion matrix? Not at the moment. I'm sorry, because we have a lot of other, a lot of topic to cover actually. Right. So I'll check, at the end if it is possible. I would definitely try to show confusion matrix for the same problem currently. So number of epochs and number of iterations, how many times you want to train them, right? So I want to train them for 5 iterations, 6 iterations. So that means the whole 600 images or 500 images will be fed to the model 10 times. So first time, second time, it's like what? When we were kids, we were learning ABCD. So we finished the whole book first time, second time, third time. So we read the book 5 times, then we become very good at that. So epoch is like how many times you read the whole book from first page to last page. Similarly, how many times you feed the same data to the neural network, that's the number of epoch, right? So you want to feed the same data 10 times, right? And each time the performance should increase, right? It's like first time when I read the book, my accuracy might be less. Second time I read the book, the accuracy may go up, again up, like that. So we are making the neural network read the whole data, learn from the whole data 10 times at the moment, which could be higher than that as well. And batch size 100 is what? At a time, we will not pass all the 500 images, right? Because whenever you use it to read the book, you don't read the book all at once. You read 10 pages today, 10 pages next day, 10 pages next day in a batch. Similarly, we are feeding 100 images and then 100 and then 100 and then 100 like that. And that's how it is completing one epoch, right? So it is taking total 5 iterations to complete one epoch. I have answered the question. And what is Adam optimizer? So Adam is a modification to a very popular optimizer called gradient descent. So gradient descent is used to update the values of weights and bias. So it will update the values of filters, it will update the values of weights so as to minimize the loss, which is the error. right? So that's the idea, right? So Adam is a modified version of gradient descent optimizer, which is, and the benefit of using Adam is that in normal gradient descent you have to manually pass the value of learning rate. In Adam you don't have to, it automatically tunes the best value of learning rate. Okay, gradient descent algorithm is an approach. How do we optimize the weights and bias of neural networks by reducing the loss or the error of the neural network? I hope that answers the question, Anil. Let me know. One forward plus backward propagation in one epoch? No, Abhishek, it would happen in one iteration, right? So you see, within one epoch also we have batch size 100. That means in one epoch there will be 5 iterations. That means one forward and backward pass happen 5 times in one epoch. Abhishek, I hope you're good, because in one epoch we are not feeding all images at once. We are feeding 100 images and doing the whole process. Again 100 images, doing the whole process. So in when you feed one batch, the forward and backward will happen. Another batch, again forward and backward will happen. Another batch, and again forward and backward will happen. That means in one epoch 5 forward pass and backward pass will happen. The backward propagation will happen. I hope that answers the question. Abhishek, right? You mean lesser batch size, higher the epoch. You know, the batch size heavily depends on what is computational capacity that you have. Technically, you would want to keep higher batch size, not very less. Higher the epoch is definitely better, right? But how many images can you feed at the moment to the neural network? It depends on how much of computational capacity that you have. If it is a time series data, higher batch size helps a lot. Should we be using ReLU for the hidden layers and binary entropy, categorical cross entropy on the output? Yeah, so ReLU for be used for hidden layers, and for the output layer, it depends on what is the problem. So if I'm using my problem is 2-class classification. For the output layer, binary, sigmoid will be activation function. If it is multi-class classification, let's say if it is like 5 or 10 class classification, Softmax will be the activation function, and categorical cross entropy will be the loss. So for sigmoid, binary cross entropy. For Softmax, categorical cross entropy. That's the idea whole. Juhi, in every step the accuracy is increasing. In every step the accuracy technically should be increasing, and the final judgment technically how do we take is the epoch in which we had the most closest accuracy between train and test, and the highest one, the highest and the most closest. These are the two principles based on which we check that we may want to save the model or use the model from which particular epoch. Okay, so that's an idea, everyone, and it's going slow at the moment currently, right? So again, at the moment, as you can see that why 5 iterations in each epoch, Amani. So the idea is that we did the splitting of data into train and test. 25% of data we used for test, right? So if I look at the 75% of 606 total images we've had was 606. That means in train we have somewhere around 454 images, and rest are in test. So if I use a batch size of 100, so first 100 images will go, second batch, third batch, fourth batch, and it will take total 5 iterations to finish all the 454 images, right? As we are using, so in one epoch is what? You train the neural network with the whole images. So I have 450 images as a part of my train data, right? So to train the neural network with whole images, I cannot pass 454, I'm passing a batch of 100. So it'll take 5 iterations to finish 450 images with a batch of 100, right? So number of iterations are equal to total volume of data divided by the batch size. Okay. So as we can see, still everyone, the idea is that we have overfitting on the model. We could improve the performance of the model from the last time a bit better. Now we have 72% accuracy on train data and 95% accuracy on test data, right? So which is a bit better, but still it is challenging to get good performance on the top of this, right? So this is where we'll be shifting to the idea of transfer learning now. It's time to get ahead with that, right? So before there's a question, let me answer that. The train model is training at 90%, where test is 70%. This is, was that an effect of convolution? Yes, that was effect. There was effect of a bit of change in architecture. So I tried out improving the segment of feature detection. I can also put some effort in improving the classification segment as well, Vishnu, right? So we have to yes, change in architecture will definitely impact the overall performance of model. So we have to spend a lot of time in tuning the performance, tuning the architecture of model to get the good performance. That's where the process of computer vision or image classification becomes very computationally and time-wise expensive process, right? You have to spend a lot of time in improving the overfitting, improving the underfitting, optimizing the architecture of model, and get to a good architecture. This is an art of a researcher or a computer vision engineer, right? This is the skill somebody has to have. Yeah, so you need to get the best architecture which can give you best model. Are we good with that? So yes, this change is the yeah. So that change is the change in architecture. The change in performance is the result of change in architecture. So now still we don't have very good model, very much satisfactory model. So this is where we're going to shift to the idea of transfer learning. Are we good to go ahead and shift to the idea of transfer learning, everyone? So I'm going to take another 30 minutes of your to finish this topic of transfer learning and get to the point which we wanted to actually reach out at the moment. Okay, so I hope we're good to go ahead at the moment, right? So let's go ahead with that, and we're going to talk about something called what is transfer learning. So let me bring you a context over here of transfer learning to help you understand that, and that would sort of give me a quick idea, help us to understand. We'll take an example to help us understand, what is transfer learning and how does it works. Okay, so let me explain you a scenario. Okay, so it was a time back in 2017 or 18 in the beginning, or I guess 17, and it was. We're working for a company based out of Bangalore, and so we can say that, let's say the name of my company was ABC. Okay. And we were actually, yes, that's also possible, Balakrishnan, right? So maybe those who are into biomedical or medical fields, I guess the current topic is going to be very much interesting for you, right? So let's, listen to this part. And yes, you can do EEG signal classification as well quite easily with the same neural network. It just, if your signals can be represented in the form matrix, you can use convolution neural networks. If it is not represented in the form matrix, if it is array or vector, then you can use simple dense layers, dense neural networks, or even LSTM networks as well. Okay, so coming back here. So let's say I was working for a company ABC. I can't reveal the exact name. But yeah, we had a client which was an FMCG client. So FMCG client is, it was, let's say an example could be Coca-Cola. Right. So we had FMCG stands for fast moving consumer goods, like shampoo pouches, like cold drinks, like snacks. These are all part of FMCG products. Now, our company was actually doing marketing. So we were into marketing and designing marketing plans for FMCG clients, let's say Coca-Cola. Now this company, our client, right? So this is our client. And our client spends a lot of money in multiple channels for marketing, right? So they use marketing because their sales heavily depend on marketing, right? So they do marketing and their sales heavily depend on marketing. So they do outdoor marketing. So you might have seen a lot of hoardings of Coca-Cola around the cities. They do marketing via sponsorship to event, like IPL, Pro Kabaddi, a lot of these events they sponsor. They do marketing via getting endorsement from celebrities, like Bollywood or cricket or sports celebrities. They get endorsement from those celebrities to market their products. But on many of these tracks, the budget, they spend a lot of money on the marketing part, but at the same time, they don't spend money on one channel only. They spend on multiple channels, but they are not able to know that which of the channel is more fruitful. Right? So are we getting more sales because of outdoor? Are we getting more sales because of sponsorship to the events? Are we getting more sales because of endorsement to Ranveer Singh or Ranveer Kapoor or maybe Virat Kohli or Mahendra Singh Dhoni? So what is generating more sales or what is generating less sales? They were not able to track ROI, the return on investment. Right? So they were not able to track exact ROI from a specific channel. So what is the ROI from outdoor marketing, what is the ROI from sponsorship to event, and what is the ROI on endorsement? Because marketing is just to increase the visibility of the brand, right? Increase the impression of the brand among the customers, and they were not able to exactly get the actual ROI from each and every channel. So are we good with the problem what the client was having? Right, they were not having any clear idea about the return on investment that they make via multiple channels of marketing, outdoor sponsorship to events, endorsement, and there were even more channels, right? So that was the issue that they had. Are we all get with the issue here, right? So I'm just going to bring you to the logic where we can talk about transfer learning. How did we do that? Okay, so to solve this issue, the marketing team of the client itself came up with a solution or a situation is that our main customers are, right, that means Coca-Cola. Let's say that those people who use Coca-Cola are not kids, so people less than 18 do not consume this brand a lot, and people who are more than 18 and generally people who are more than 50, they don't consume this brand a lot. So most of the people who are into the group of, let's say, 80 to 45 consume this brand a lot, and these people spend a lot of time on social media, right? So their consumers spend a lot of time on social media, so they want to check that how is our impression improving on social media. So we had to build an instrument which can help them understand which particular channel is investment and how much of investment is helping them to get the actual ROI on social media, right? So what we had to do is, let's say one of the channel we picked first was Instagram. So we had to get all the images every day. So we had to capture every day all images from Instagram, which might be tons of images that we get on Instagram every day. From these images, identify the name of or the logo of event, celebrity, right, which could be Ranveer Singh or Virat Kohli or Dhoni, and then the brand. As part of brand, we need to identify bottles, Coca-Cola bottles, logo, all of this. So we were identifying that today the visibility of IPL was X, 20% on Instagram, and the visibility of Coca-Cola was 10%. The standard visibility of Coca-Cola without any event, without any on the normal day is 8%, right? So we calculated standard visibility of Coca-Cola. On Instagram it is 8%. Then we every day calculate that today the visibility of IPL on Instagram is 20%. With that visibility of IPL, how much is improvement in visibility of Coca-Cola on Instagram? And that was helping us to calculate ROI on making investment to IPL. Similarly, the standard visibility of Virat Kohli on Instagram is 10%, but when he's into cricket match or anything like that, with the increase in his visibility, are we getting increase in visibility of Coca-Cola or not? Similarly, when there is a movie from Ranveer Singh, with increase in visibility of Ranveer Singh on Instagram, is there an increase in visibility of Coca-Cola or not? Now, in order to develop this instrument, we had to identify all the bottles of Coca-Cola, and we didn't have any images. Okay, so one of the biggest challenge that we had is with no data, you need to build a neural network which can identify Coca-Cola bottles, which was a big challenge. To solve this problem, we, because they don't capture data and they don't capture pictures. So we did web crawling, and anyhow we were successful in capturing with some campaigns as well. Post your pictures with Coca-Cola and get a 10% discount voucher, or get a chance to win some prize, or meet Virat Kohli, something like that. So the company did some campaigning, and we could capture around now 5,000 pictures of Coca-Cola bottles with those campaigns. So now we had 5,000 pictures, and the task was to build a model which can identify Coca-Cola bottle and the logo. We were still able to identify, but bottle was a big challenge. We were not successful in terms of identifying Coca-Cola bottles effectively or efficiently, which was a big issue for us. And this is where the whole process was actually kind of paused for a quite of time. And that was a big challenge for us, right? So we were not able to use 5,000 images and build a model which is sufficient to identify Coca-Cola bottles from Instagram. So this was a big challenge. Are we good with the challenge here, everyone? The main challenge with 5,000 images, which is less volume of data for us for the complex problem, we were not able to differentiate between all the bottles, identify the bottle and the bottle which is Coca-Cola. right? So one of the challenges with from other background, from human and everything, we have to identify the bottle, and then whether that bottle is a Coca-Cola bottle or not, that also was a challenge. So are we good with the issue here, everyone? Right? So what we did is we found out that, well, in Europe there is a similar beer company which has built a model to identify beer bottles. And they used neural network, they used CNN, convolution neural network. And they released the pre-trained neural network, the trained neural network, and they trained it from around 50,000 images. And they released the trained neural network on GitHub for free. What we did is we took their neural network. So we took the neural network, the CNN, for beer bottles. Now bottles are bottles, right? So the feature detection segment of their neural network was very powerful in order to identify a bottle. And then the classification segment was identifying that whether that bottle is a beer bottle or not. So what we did is we took their CNN and modified it and then trained it with Coca-Cola bottles. As the CNN was already trained on beer bottles, it was very effectively able to identify different features like the cap of bottle and all different features of bottle, general bottle. And then it was, we have to just train it to identify Coca-Cola bottle. So we trained that, and then we were successful, and our accuracy improved up to around 86 to 88% to identify Coca-Cola bottles. This process of using a pre-trained neural network, which was trained for a similar task, and consume it for your task, is what we call as transfer learning. Okay, so we consumed a pre-trained neural network which was designed to identify beer bottles, and we trained it to identify Coca-Cola bottles. After a bit of tuning modification and training with new images of Coca-Cola, that was, this process is called as transfer learning, right? So are we good with the context of transfer learning, everyone? Okay, so this is what we call transfer learning. Transfer learning is a process in which you use a pre-trained neural network and try to adapt that for a new task. We humans do this a lot. Let's say if you have to hire a driver, will you hire a person who has never driven a car, or will you, let's say I have a car which I don't have, Audi, or let's say a BMW, right? So I don't have a BMW, but let's say if I have a BMW, and if I have to hire a driver who can drive my BMW, so technically, would I hire a person who don't know driving at all and train him to do driving and learn to drive BMW? Or I would hire a person who has at least experience of driving Honda City, all right? Because if he has or she has experience of driving a Honda City car, that means they know how to drive a car. And it would be easy for me to make that person adapt how to drive a BMW, right? So whenever I have to do a task, we generally humans take a person who has a little experience on that, and they use their past experience and adapt the new task quite easily. This is what we call transfer learning. So in human analogy, we use a lot of transfer learning. We always use our past learning to do a new task, or past experience to do a new task, right? So that's called transfer learning, right? So we humans do a lot of transfer learning, and this is a way to implement transfer learning in machines and computers and neural networks, right? So transfer learning is a process in which you use a pre-trained network and help it to adapt new neural network or a new task. And in this process, you can get good performance with less data, with less effort, because this company which have developed the beer bottle neural network would have put a lot of efforts in optimizing the architecture of it. Now, I don't have to put that much effort in improving the architecture. I don't have to put a lot of efforts in capturing huge data. And in lesser time, with lesser data, with lesser effort, I can get a good model. That's the benefit of transfer learning. That's the reason a lot of companies ask for experienced people and they don't hire freshers a lot, right? So this is what we do in transfer learning. So this is deep learning algorithms. Yes. This is what we do in deep learning. So this question is this where deep learning algorithms develop the frontier of reinforcement learning? No, not like that. Reinforcement learning has a very different, a bit different architecture and aspect as well. But yes, in reinforcement learning, we also use deep neural networks and all. But this is a different approach. In reinforcement, there is a continuous feedback process, which is not here. All right, so let's now go ahead and talk a bit more about transfer learning to have more clear understanding of how do we do this and where to get such pre-trained network, right? So you may have a question about where do you get a pre-trained network for your process, and second is how to do this. and how to do modification, how to tune it. So we're going to see a practical example of this process, right? So this is going to be quite interesting and you're going to love this, right? So we're going to be seeing a practical example of pre-trained neural network. How do you bring it, modify it, and do your task? So for our 3-class classification problem, we couldn't get good accuracy. Now we will be able to get good accuracy by implementing transfer learning. Yes, so we're going to see that what kind of changes we need to do if you're using transfer learning. So here we go. So there could be 4 situations in which you may want to implement transfer learning, right? So there could be 4 such situations where you would want to use transfer learning in general, right? And those situations are mentioned here. You can see. Let's understand them. Okay. So what are the 4 situations? The first situation is that you have very less volume of data for your task, right? So you have very less volume of data for your task, and eventually you could find a neural network which was trained for a similar task. Right? Or let me explain that with a different, this chart, right? So there could be 4 situations in which you may or you may not want to use transfer learning. The first situation is that you have small data for your problem. You have small data for your problem, or you may have very good volume of data for your problem as well. So currently the first situation is you have small data for your problem, but you could eventually find out a neural network which was trained for a similar task. So my job is Coca-Cola bottle identification. I could a neural network which was tailored for beer bottle. That means I got a neural network which is tailored for similar tasks. This is the most promising situation where you would want to use transfer learning, right? So this is first combination of situation. The meaning of this we'll discuss. Second situation is you have small volume of data, but you tried hard. You couldn't get a neural network which was trained for a similar problem, but I could get a neural network which was trained for a different problem. So I'm doing Coca-Cola bottle classification, but I got a neural network for face recognition. So face recognition and bottle identification are 2 different tasks. This is the second situation. Third situation is you have large volume of data for your task, and you could also find out a neural network which was trained for a similar task. This is third situation, right? You have large volume of data for your task, and you got a neural network which was trained for a similar task. The fourth situation, or the most unlikely situation to use transfer learning, is you have large volume of data for your task, and you got a neural network which was trained for a different task. That's the fourth situation we have. So these are the 4 possible situations, and we're gonna see in all these 4 situations, what should you do? Excuse me. Are we good with the 4 situations, everyone? Are we all good with the 4 situations? Let me know. So I hope we all good with the understanding of all the 4 situations. Small data, similar neural network you have. Small data, different neural network you have. Large data, similar neural network. Large data, different neural network. Let's now go ahead and see the solution in all the 4 situations. How should you use transfer learning? Here we go. So let's say this is our pre-trained network, right? This is our pre-trained network. Consider that. It has multiple convolution and pooling layers. So convolution, pooling, convolution like that we have. Generally, when you have multiple convolution layers, this is very important everyone to understand. Initial layers will understand low level features. So this is, you can say, low level features, which is HS. Next layers will understand or will learn a little high level features like shapes, like nose, ears, and all. Next high layers will understand very high level features, right? So very high level features, which is like the shape of the pictures and all. And then you may have a lot of convolution layers as well. This how could be your, how your pre-trained neural network could look like. Right, so what do you do in the first situation? So let's talk about the first situation where you have small data set for your problem, and you have a similar neural network. You have a similar pre-trained neural network. In that situation, you can say when you have similar neural network, can we say all the layers of feature detection are useful? Feature detection is completely useful because you have a similar neural network. What you do in that situation is just clip out or remove the last layer of neural network. It may be possible that this neural network was designed for, let's say, 5-class classification problem, but I want to do 3-class classification problem. So what I have to do is I have to just remove the last layer, add a new layer with 3 neurons, add a new layer with 3 neurons, right? And freeze all the previous layers. So freeze all the previous layer, freeze them. That means make them untrainable. Only keep the last layer as trainable, and train neural network with your new data. So what I will do is I'll bring the beer bottle neural network, remove the last layer, add a new layer, freeze all the previous layers and train the neural network with the data of Coca-Cola images, and we'll be able to get good model out of this. Okay, are we good with the to-do task for the case 1? Right, small data, similar neural network, right? I hope we're good with that, everyone. Right, so what sort of approach one should use when it comes to you have a small data set for your problem, but you have a similar pre-trained neural network, right? So you should sort of pick that and try to remove the last layer, add a new last layer, and add a single new last layer. So you can add one, you can add many as well, Abhishek, right? It's up to us. And freeze all the previous layers and try to, try to sort of train the neural network out of that, right? So yeah, that's more of an idea. That's more of an idea that the way how do we do that. Are we good with this, everyone? Okay. So here we're good, right? The other neural network, I mean, for other situations, there can be other, other guide or other options how you may want to do. For example, when you have different neural network, which is trained for different problem, in this case, all of these layers are not useful. So we remove all the layers, add a single layer, and keep all of them, freeze all these layers. So freeze these two and train the last layer. So when you have when you have different neural network, you remove all the last layers. In fact, just keep the initial convolution layers, because you can't take benefit of these layers because your neural network is different, right? So I can't take benefit of these layers. These all are not useful. Highest level of features are not useful at all. You remove them, add a single dense layer, and try to train the neural network. But you freeze all the convolution layers initially. For third situation, which could be you have large data, but you have similar neural network. When you have large data, you again remove the last layer, add a new last layer. At this time, you don't freeze them. Keep all the layers as trainable layers and train the whole network. Because your large volume of data, you can fine tune that and you can achieve great performance in current scenario. So you don't have to freeze them. The only difference in this case and the first case was you don't freeze the previous layers. You keep them all trainable and you train the whole neural network. Right. And the fourth situation, which is the least unlikely situation where you may want to use transfer learning, is your data is large and your problem is different from neural network. So here you may want to sort of remove the last layer, add a new last layer, and you just copy the architecture of neural network, right? So these people who have spend a lot of time to develop the architecture, you just copy the architecture, initialize your weights again randomly, and retrain your network. So you're kind of copying the architecture of the previous model and trying to train the neural network, right? So that's the idea of it. Are we good with that, everyone? Right, so that's understanding. Now the question could be, how do I get pre-trained neural network? Let's talk about that as well, right? So back in 2006, where the world of computer vision was flourishing up, which is like 14 years back from now, Fifi Lee, who happens to be currently chief data scientist of AI/ML at Google Cloud, and she's also a director for Stanford AI Research Lab as well. So Fifi Lee and again few other people who actually decided to help the industry or the field of computer research to improve it up. So they come up with a very popular idea of helping industries to improve the research in computer vision field and also compete them to each other. Let's say that Google wanted to know that what Microsoft is doing, Microsoft wanted to know that how good the AI team of Google is, and they both wanted to know how good the AI team of Intel or AI team at Stanford University or Toronto University is, right? So a lot of enterprises wanted to know this, and they wanted to know that what they are doing it or what we are doing, how good our team is. All of them want to have this idea when they were actually hiring the people for AI development, right? So that is where Fifi Lee came up with a idea called ImageNet, right? So they came up with the idea of ImageNet. So ImageNet was actually a competition, right? So she came up with an idea of ImageNet competition. So ImageNet competition was a collection of initially it was 10 million images. So they set up a team which crawled web on Bing and Google search and collected around 10 million images. They labeled it, all the 10 million images, and this was the ImageNet project, which is a large visual database designed for object recognition software research. So they prepared a database of 10 million images with label, the object boundary as well, the segmentation as well. And then they launched the competition ILS-VRC, ImageNet Large Visual Recognition Challenge, which was launched in 2010. So they took around few years to prepare the data set for that. In 2010, they launched this competition, and a number of research organizations across the world participated in this competition till 2017. And till that moment, let's say research groups at Google, Microsoft, IBM, and Amazon, Stanford University, MIT, Toronto, research organizations from all the countries, India, China, all of them participate in these competitions. And they developed state-of-art neural networks, optimized them with the best research involved, and trained on the ImageNet data set to get good accuracy, right? It was around 10 million images, which is very large volume data. The teams at Google and Microsoft, they wanted to check that how good and how powerful their team is, how good they are learning, and how good they are growing up. In order to do so, they allowed their team to spend the whole year and around 6 months on same competition without doing any work and check your capacity, right? So the teams at Google, Microsoft, and all of these organizations, they spend millions of dollars on training this model to capture the good infrastructure, a good amount of RAM and CPU and GPU, all of these infrastructure requirement. And a lot of high-end researchers, they spend their time to participate in these competitions, right? In 6 years, a lot of research competitions participated. Back in 2014, a team from Google developed an application or a neural network called GoogleNet, right? So they developed something called GoogleNet in 2014. And they also, in order to check how better can we, how much accuracy can we improve, how much error rate can we decrease, they also made a set of humans manually do the classification. So humans manually do the classification, and they calculated the human error rate is 6.8%. That means if humans are shown this 10 million images, how correctly they'll be able to identify the classes. So there was 6.8% error. So the data set was initially 10 million images with 1,000 classifications. So there were 1,000 class classification, right, which is a very heavy problem. 1,000 class classification, that means you have 1,000 different types of classes you have. And the human error rate was 16.8%, and GoogleNet could reach up to 7.2% of error rate. So they almost touched the human error rate. And then in 2015 or 16, ResNet came into picture. ResNet was a team of researchers from OpenAI, supported by Tesla Motors, and they surpassed human error rate, and they reached to error rate of 5.2%. That means their model ResNet was even powerful than humans to be able to do right image classification. The error rate of ResNet was 5.2, whereas standard human error rate on the same data set was 6.8%. So this all, VGGNet was again a set of researchers from Stanford, and there were such models available. AlexNet as Toronto University. AlexNet was the very first model which won this competition, and in subsequent, where the last winner is ResNet 50 or ResNet model. Inception from Google, GoogleNet from Google. All of these models were trained and they participated in this competition. At the end of the 2017 or 16 end, all of these researchers and the ILS-VRC organization open sourced all of these pre-trained network. That means all of this pre-trained neural network, which organizations spend millions of dollars and they spend whole year to prepare them, develop them, optimize them, they open source this. This act of open sourcing these all models accelerated the growth of deep learning in last 5 years. In last 5 years, you might have seen a lot of companies have come up with amazing applications with great face recognition accuracy, object detection, image detection accuracy. And many of these improvement and many of this success is a result of transfer learning. So if I have to say that, out of 100 organizations which are developing state-of-art computer vision applications, at least 60 to 70 of them are using transfer learning, right? And these models are open source. We have available these models from, we have these models available on TensorFlow.keras as well. So if I have to show you that, you can access these models over here. keras.io/application. So many of these models are available over here. You can see Exception, VGG16, VGG19, ResNet 50. ResNet is series of models of ResNet. Inception, MobileNet. Inception is the same as GoogleNet. DesNet, NASNet, EfficientNet. These all are pre-trained model. This is the size of that model in memory. VGGNet is so heavy, it is having 528 MB size, and the depth of the model 126 layers. So in exception, they use 126 layers. If you look at Inception ResNet V2, it's combination of two models. They use 572 layers of the neural network, right? So there are 572 layers in that, which is quite large neural network, you can say. That is, which is very heavy as well, 215 MB of size. And these are the values of weights and bias. If you look at VGG 16, it is having around 138 million weights and bias. This neural network has 138 million weights and bias. So heavy it is, right? And ResNet 50, 25 million weights and bias, which was the winner of the competition in 2014 in the segment of object classification, object localization and detection. And it was second runner-up in image classification, ResNet 50 was. Right, so these are all models open source, and this accelerated the whole growth of deep learning. And we can use this all for, we can use these all models for a variety of tasks on computer vision and similar other tasks as well. That's the idea. There's a question: can we use this model for signal classification task? Yes, Fatma, up to a lot of extent it can be used. And there are also a lot of models available now for signal classification task as well, which are open source. You need to just make a good search on that, and you'll find such models available. And again, these models can also be used for that as well. Can we use this model for? Yeah, so you can use that in the context of transfer learning. There's a question: we need to take care of varying input shape. No, we can customize that. All of these models are trained on ImageNet datasets. So all of this model will have 1,000 neurons in the last layer. Many of these are optimized to take input shape of 224 by 224, which we can customize as well. We'll do that customization. So we're going to be using ResNet 50 as a part of that, and looking at a quick example of transfer learning with the help of ResNet 50. Let's go ahead and see that. I'll take another 10 minutes to finish this out, right? So here we go. We're going to be taking ResNet 50 to do that. Here we go with that, right? So from TensorFlow. So if I want to load this, I can say from TensorFlow.keras.applications import ResNet 50. Now to load this model, we can simply say model equals ResNet 50 dot ResNet 50. And when I say weights equals ImageNet, it will load the model with ImageNet competition weights. That means the pre-trained values of weights and bias. Let's look at model.summary. So this is where we have loaded ResNet 50 model, and you can see the last layer of ResNet 50 is using how many neurons? Last layer is using 1,000 neuron, and it is having total 25 million weights and bias. ResNet 50 is, and the last layer is using 1,000 neuron. This is the whole architecture of the neural network, which you can see that is very lengthy as well, right? The architecture of the neural network. This is the whole. This ResNet 50 was designed to accept data input of the shape 224 by 224 by 3, right? So it was designed to accept input shape. Or images of shape 224 by 224 by 3, which is the input layer. And then there are a lot of other layers. You might have seen these layers, many of these layers: batch normalization, add layer, batch normalization, activation function layer. They use separate layers, and a lot of other layers as well in this neural network to optimize that. We can use this ResNet 50 to train our data and customize this ResNet 50 and do the task of 3-class classification for our use case. Let's do that. We'll again use load ResNet 50, but before that, we'll define the input layer, right? So now we'll use a different architecture. We'll define input layer equals layers.input, and we'll mention shape is 200 by 200 by 3, right? So 200 by 200 by 3. That's the shape of data that we'll be mentioning up, right? Just a Okay, so I started getting knocks. I have to finish this. I have to catch another meeting, right? So I'm going to take a bit quick, everyone, right? So input layer is going to be layers or input. We have defined the input layer. Now we're going to add the, we're going to load the ResNet 50 model. So we're going to say model equals ResNet 50 dot ResNet 50. We can mention include top false. So when you say include top false, it will remove the last layer of the neural network, which is of 1,000 neuron. So you can see that last layer of the neural network is how many? 1,000 neuron, which you don't want, right? We have a 3-class classification. That means in our neural network, we want last layer to be of 3 neurons. So include top false will remove the last layer, and we can say weights equals ImageNet, and we can say input underscore tensor equals input underscore layer. right? So now it will optimize and synchronize this neural network with to accept it 200 by 200 by 3. So Abhishek, this is how we can solve this problem of make this neural network now accept the data of shape 200 by 200 by 3. Done with that, let's see the architecture of this model. So now we don't have the neural network with 1000 neurons. Everyone, you can see that earlier the neural network was having 1000. As you mentioned, include top false, will not have 1000 neurons, right? So here we go. So now you can see that last layer is not having 1000 neurons. That's one point, right? Last layer doesn't have it. And initial layers, now you can see that this neural network is now optimized to accept input of size 200 by 200 by 3. That's how we customize them. Are we good so far even till here? Right. So you customize them, and we are able to load the neural network, synchronized it to make it accept the data of shape 200 by 200 by 3. I hope you got with this, Abhishek. You got the answer to your question, right? Now we need to add a new last layer, which is going to be of 3 neurons, and we need to freeze all the previous layers, right? So these are the 2 steps we'll be doing now. As you can see that currently the last layer is the convolution layers. We have removed almost all the dense layers from here. The last is convolution. So after convolution, we'll first adding the, first we'll try to get this convolution layer. So we'll say that last convolutional is model.output or model.output. So this will give us last layer. Now we can add the flatten layer. We can say that flat is layers dot, and this is a bit of different programming approach, layers dot flatten, and this is going to be added after the last underscore conv, right? So it is conv, and okay, so add the flatten layer, and finally we have to add the output layer with 3 neurons. So we can say that output layer is layers dot dense 3 neurons and activation as Softmax. So with Softmax activation, we added 3 neurons, and this is added after flatten. Finally, we can create a model. So final model, or you can say new model equals to models dot model. We can just mention the input. So inputs is input underscore layer, and outputs is output underscore layer, right? So now we can see new underscore model dot summary, right? So we have new model summary. So you can see that now we have after convolution, we have a flatten layer in this. So we just took that neural network and added to the same architecture, we added a new layer, flatten and dense with 3 neurons, right? So this is where we have modified the neural network, and now it is modified to do our task, right? I hope you agree with that. The same architecture of Pratima can be used in those applications as well, object detection and classification as well. Right. So here we have modified the neural network to make it accept, to do our task. So we access the last layer via output. So here we are trying to access the last layer, access the current last layer, which is the conv layer. Added a flatten after that, added a dense after that, and that's how we build the new model. All right. I hope you're good with that, Gaurav. So now next step is going to freeze all the layers. So you can see that there are a lot of total trainable parameters are 23 million, almost 23 million are trainable. We just have to make this layer trainable, and rest we have to freeze all the layers. We want to only make this layer trainable and freeze all the layers. So we can say that freezing all layers except the last layer, right? So we can say here for layer in new model dot layers, we will not go for all the layers, we'll go up to -1. So I'll say up to -1, that means it will exclude the last one. Layer dot trainable equals false means we'll make it untrainable. Now again we can see new model dot summary, and you'll find that now only the last layer is having 300,000 weights. That is only trainable, and all other parameters are untrainable. You can see that only last layer is trainable. Only these 300,000 weights are trainable, and all the layers are untrainable. So we have freezed the whole neural network. So now when I do train the model, the backward pass will only happen till the last layer. It will not go beyond that. Forward pass will happen through all the layers, but backward pass of weight updation will only happen on the last layer. It will not go on the previous layers, right? So the weights and bias of the previous layers will not change. It will remain as it is. Only the last layer weights and bias will change, right? So that's where we have made it trainable. This is where we are done with this part, and we are good to go ahead and train the model at the moment, right? So let's do that, right? Let's go ahead and train this model. But for that, we have to again do a bit of data preparation, everyone, right? Which is a bit of challenging part, but we will do that, right? So we have to do again a sort of data preparation. The reason to do again data preparation is because whenever somebody develops a neural network, they would have done some kind of pre-processing on the neural network, and we also have to do that kind of pre-processing, right? So so this is the freezing code, right? So this is the freezing code for layers in the new model dot layer. We have just made layer dot trainable as false. That means up to the last layer, that means up to the -1 layer, it will freeze that, and after that it will not the last layer it will not freeze, right? It will keep it as it is, right? So that's the idea. Please show the input layer code. I'll show the again the code part at the end. Let me just finish this task, right? So then I'll show it. So you see, the reason I have to load data again is we have to you see, the people who have developed this ResNet 50, they would have done some pre-processing on data. So we have to do that kind of pre-processing here as well. So for that, we'll say image equals. So they provide that function along with this, so that we can do the same kind of pre-processing with our data as well. So we can simply say that ResNet.preprocess input of image, and then do that, right? So this is where we have done the same level of pre-processing here. Finally, we can convert this into x as numpy.array of x, and y as 2_categorical of y, and print x.shape and print y.shape. And finally, we can split our data into train and test set. For that, we can again bring it from here. I can copy and paste the code from here, and then we can simply train the model, right? So splitting our data into train test. Now we need to train the model. So instead of the way we have written here code for training the model, we can simply use the same code with new model, right? So now we can train our new model, which is the result of transfer learning. So we'll say new model.compile with the same architecture, same same configuration, new model.fit. So let's say now we're going to train the new model, which is the result of transfer learning, and let's see how much good performance are we able to get. And it's the first epoch that started now, and let's see that. Well, what I should have done is I should have used the GPU mode, which would have done this process a bit faster. No, it's going faster, I think. Right. So or it's gonna be taking time, or what? I'm not really sure about that. So it's a bit slow. Let me do one thing, everyone. I'm gonna just open the start the GPU mode. I should have done earlier itself. I'm gonna just change the runtime type to GPU. So GPU acceleration is gonna be making it quite faster, the training process, and I will have to run the whole code again for that, right? And okay. So yeah, I need to run this again. Okay, I need to run this again. So here we go. And so I need to just train this model again, right? Because we started in GPU mode, so the processing will take a bit of time. So I just train this again, and now it's gonna go faster, right? So the moment it goes on, it's gonna go faster. In GPU mode, you can, so whenever you start with Collab, and if you're using neural networks, you should always go for GPU mode. It's going to go faster. The training of neural network is going to happen quite faster. Otherwise, in case of transfer learning, it's a very bulky model. It's going to go slower, right? So we don't want that to happen. So we have started with GPU mode, and in a moment, it will start executing all the codes, and then it will come back to here, this one, and make it happen faster. So let's see that where it is stuck at the moment, or what is happening. Okay, it's at the moment previous model is downloading the model, and here done we are, and starting to train the model. So now you see it's going faster. So the first epoch accuracy 64% on train data and 90% on test data. And in subsequent epochs, now you can see that we are almost getting 99% accuracy on train and 98 on test, 100% on train and 98% on test, right? So yeah, so at the end, we can see that we got 100% accuracy on train data and 98% accuracy on test data, right? So using transfer learning, what we could get here is, everyone, 100% accuracy on train and 98% accuracy on test data, right? So as you can see that, we will talk about the code part, everyone. So all the questions that you have. So are we good with the idea that, with the help of transfer learning, we could get much better performance compared to what we were getting without transfer learning? Do you agree with that? So do you agree with the fact that by using transfer learning on the same data set, we could get better performance, 100% accuracy on train data and 98% accuracy on test data, right? So I hope we're good with that. So this completes the complete logic of expected part of this workshop. Now I'm going to answer the questions, right? And we'll have to make it a bit quick. So what I have done just in here is, you see, whenever you use transfer learning, the people who would have developed this model, they would have done some pre-processing to their data while they develop their model. Now, when you want to use their model, you would want to do same pre-processing on your data as well. So with the package, they also provide the function which has the pre-processing that they have done. So by ResNet 50.preprocess input, we are also doing the same level of pre-processing on our data, right? So that's the reason we had to load the data again. Are we good with the logic, Justin? I hope that answers the question, right? Juhi, the input data code is here, right? So this is where we define the input layer and try to sync that. It's here. So not this one. I'm sorry. Yeah. Yeah, this one. This is where we did that. Okay. So done we are, everyone. I hope we're good. Any question you have? Okay, so now we are good to go ahead with questions. You can ask questions. I hope we're good with this part. So I'll be sharing all the notebooks, and I'll be sharing the, you will be receiving the videos and notebooks as well, the programming notebooks over email, right? Which you can go through, and for any question, you can come back to us. So that was about it, everyone. That was about the particular webinar and the workshop for the 2-day, and it will work for 32x32 as well, Humaira. You can just resize your accordingly, your data to that size. It will work for that as well. Not a challenge at all. Right. So thank you all for your time. And yes, we are open to questions. Any question you have, we are going to go ahead with that. It just will not be able to go a bit more into code, but yeah, now we are into questions part. So yes, open to questions. All right, if you have any. So so we have even more workshops coming up. So we are planning for one more workshop on object detection as well. We'll be updating you regarding that. We are also planning for some FDP, faculty development programs. So if you happen to be a faculty or an IT professional, you can also join such programs as well. You can get more details of that from our, the sales team and the other team members at our company as well from Tech Ventures, and you can connect to us for that. Right. So that's more of an idea, everyone. Right. So yes, any question, any doubt you have, let me know. So can we use transfer learning for better optimum values of reinforcement properties like Markov process? Yes, Vishnu. In fact, it just, The only point, Vishnu, is that transfer learning has very much scope in computer vision. So you have a lot of good models available in computer vision. Technically, you can use transfer learning in almost everything, right? But you have a lot of good models in computer vision. In last 3 to 4 years now, you also have good models in natural language processing as well. For text and for speech as well, you have good amount of transfer pre-trained models for transfer learning. But we may, at the moment, we may not have very good models available for transfer learning, for reinforcement learning, but technically it is possible, and people have been doing this. It just, you need to find the right source to get the good model out of it. Okay. So that's the answer to your question, Vishnu. I hope you're good. There's a question: what is the project work that we can work on? Well, a lot of examples you can work on is good. That could be possibly image segmentation. There are a lot of good challenges available in Kaggle. You may be interested into that, and you can work on that as well. Right. So yes, you can send some questions via email to us at contact@technic.in. We would be happy to reply that. Okay. So yeah, that's an idea, and. For the certificate regarding this workshop, you need to connect to your point of contact or drop us an email on contact@technic.in. So whosoever is your point of contact, as there are multiple people, so whosoever is your point of contact at the Tech Ventures, you can connect to them and get help regarding any other detail about upcoming sessions or certificate or any other upcoming paid workshops or certificates as well. So yes, we are planning for FDPs in coming month possibly, or maybe at the end of June, or maybe in the mid of June. The dates are not yet fixed, but yeah, you will be definitely receiving some notifications regarding that. In a video, I mean, in the frames, many object. So there's a question: in a video, I mean, in frames, many object may be there. How will the model be learned? We can use in object detection or flash classification. So you see, Pratima, the first part of feature detection is going to be same whether you talk about one object or multiple objects. Now, for detecting multiple objects, there are different modification to CNN. One of the modification to CNN is RCNN, which is region-based CNN, right? So I hope you would want to explore the idea of RCNN. It's a very popular approach developed by an Indian researcher, Jitendra Malik, Professor Jitendra Malik, working at University of Toronto, developed RCNN or region-based CNN, and a modification this is faster RCNN, which is very popular model for such application. And then a even better model is SSD, single shot multi-box detector. That's also a very popular model for multiple object detection in image frame, and that could be applied to videos. It just in standard RCNN, it takes around 47 seconds for one image processing and detecting multiple objects, whereas faster RCNN takes 2 seconds. But in video, you have a speed of 30 FPS or 40 frames per second. So you want to go for SSD, which takes around, which can process around 59 frames per second. So the speed of SSD higher, but the performance of faster RCNN is higher. Faster RCNN is higher. So if I have to apply it on video, I would want to go for SSD, which is a bit less accurate, but can process higher volume of frames per second. Right. So that's the idea. Sure, we have a lot of other similar webinars and workshops coming up. I hope you must be interested into that. So you'll be getting notification to that. You can also connect us on our Facebook page of Tech Ventures, and there you can get a lot of details about upcoming webinars and workshops. Right. And yeah. That's an idea. So thank you very much, everyone, for your good feedbacks, and that is very much satisfactory. Thank you very much. Thank you. And can you please suggest where can we get MRI data? Yes, you can get. There is a very popular competition. I'm just not able to recall that. If you can drop me an email, Rahul, or maybe connect on LinkedIn, I can help you out with the link for MRI data. Right. So yeah, I have actually a source where I can possibly show you an example. I'm not sure. Just to check. Right. So not this one. I think I don't have it now, but if you can drop me an email or connect on LinkedIn, I can definitely help you out with that. A bit of source for MRI data. Sometimes we struggle in getting the data set for different domains. What is the way to find them? Well, there are very good sources to find data sets. One is that you can find out it on Kaggle. Kaggle is a very good repository of data set. Another is UCI machine learning. This is a very good repository of data set. And third is you can also do dataset.research, right? So there's a repository like dataset.research.google.com. So this is a Google search engine just for searching data set, right? So part of Google which is used to search only data set, right? So here you can search data set. So let's say I want MRI data, Rahul, so I can simply search for MRI data here, and this will give you data set for machine learning and data science, right? So MRI units per million by country and magnet reasoning imaging data set, right? So this gives you data set for that. The URL is dataset .research.google. So MRI and S- Kaggle datasets are quite good. You can get all of them available over here. There's a very good URL that you would want to consume for dataset search. I'm pasting the link in the chat box. All right. So yeah, this is where you can find out a lot of it. I can share the Facebook page link possibly. Yes. So this is our website. You can come to our websites. We have some few free courses as well if you want to learn robotics or something for students, right? Or you can encourage your students as well to get on some free courses on our website as well. I can actually suggest you with some Facebook links or the links to the social media plugins because we stay a lot active on Facebook and help publicize all of our I would say all of our events on Facebook, right, that we regularly do. And I can share you with the link of Facebook page, which is I guess this one. There's a link to our Facebook page. In case I'm missing any question, you can please ask them again. Right, so yeah, that's the idea. We'll look into RCNN, fast RCNN, and then SSD, right? That's great. Okay, and like I'm planning to work in, okay. So yeah, you can get the data for agriculture as well on this link, and a lot of data sets over there. So Guru, I have pasted the link, and my LinkedIn ID is, I guess it is, right, and I'm not, just a second. So yeah, it is this one. I'm posting that in the chat box. So yes, that's the idea. What is the best data set for facial emotion? Please suggest me. Yeah, they are good data set. I have one of the Yale Faces data set. So I used a long back data set called Yale Faces, but it was very small data set for emotion detection. But then there is a very popular data set, I guess, available somewhere on internet. I'm not sure with exact source. If you can drop me email or connect me on LinkedIn, I can help you out with that. Other than that, this dataset search engine is going to help you out a lot with that. You can search anything or any dataset over here. You'll get about it. Right. So that's an idea. And there's a question. Can you introductory session for students to develop their interest in upcoming field and they're not aware so much in depth? Yes, definitely. We are actually planning for such things, and I would encourage you all, if you want to organize anything, any event for students like that, we're organizing a lot of free workshops and boot camps for students. You can get in touch with our manager on this, right? So I'm sharing his contact over here, right? So not in this one, my bad. So I'm sharing his contact over here. The manager, Sagir, his name is, and you can get in touch with him. He's going to help you out to arrange such events for your college or your students in case you want on a specific topic, right? So link to Facebook as well. This is our Facebook page, and you can also get the link to that. Okay, so I have posted the link for Facebook page as well. You can connect to us on that. Okay, so yeah, that's an idea. Will transfer learning dataset be a new paradigm of education in varying engineering college platform in following decades? Yeah. So Vishnu, yes, at least this is very speedily changing the way people consume AI or deep learning, I would say. right? So transfer learning is also now very widely used in NLP as well. And when it comes to education, yes, the education paradigm is going to shift a lot, not only with the help of transfer learning, but the deep learning algorithm, the research, the application development, and the part of tuning and programming part as well, right? So a lot of research paradigm is going to shift to that level as well, for sure. And it would take a bit of time, but yes, not only transfer learning, but a lot of other related topics it's going to shift to. That's my intuition and understanding at the moment. Right. So yes, that's the idea, everyone. I hope we're good at the moment. And any question you have, let me know. Okay, so I believe we are good so far at the moment. With this part, we'll be ending up here. Thank you all for joining the session, and it was wonderful having you all, because I like the way you ask a lot of questions. So when people ask questions, it becomes more. It looks like people are making sense and they are understanding, right? So that's a very good thing. So thank you all for being an amazing audience, and see you all in the upcoming webinars. Bye bye and good day.